Hello there and welcome back to the Sleep Science. You float in the dark, and ahead of you the sun hangs like a molten coin pressed against black velvet, its surface rippling and boiling as if it's alive. Because it is. You can almost feel the heat licking at your face, even from 93 million miles away, and yet something about tonight feels tense. The sun seems restless, like a giant engine revving a little too high. And here's the uncomfortable truth. You probably won't survive this. Not because the sun is about to explode tomorrow, relax, but because if our star truly lost control, life as you know it would be a toasted marshmallow in cosmic seconds. Comforting, right? Still, you hover there, watching rivers of plasma arc thousands of miles into space. The surface churns at about 5,500 degrees Celsius, a perfectly normal day for a middle-aged G-type main sequence star. Deep in its core, hydrogen atoms are being squeezed together through nuclear fusion, forming helium and releasing energy in accordance with Einstein's famous E equals mc squared. That equation, yes, the one on coffee mugs everywhere, is the reason you're warm, awake, and capable of overthinking text messages at 2 a.m. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And as you settle in, let me know where you're listening from and what your local time is. I love imagining this story drifting across time zones like cosmic background radiation. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You drift closer, in noticing that the sun is not a calm ball of light, but a storm. Its surface, the photosphere, seethes like oatmeal left unattended. Except this oatmeal could vaporize continents. Every second, the sun converts about 600 million tons of hydrogen into helium. That's a mainstream astronomical fact, one confirmed by decades of neutrino detection experiments. Tiny ghost particles called neutrinos stream from the core and pass straight through your body by the trillions each second. Don't worry, they're harmless. Think of them as the universe's most socially awkward messengers. But something feels different. Astronomers have noticed that in recent decades, solar activity has behaved in slightly unpredictable ways. The sun follows an approximately 11-year solar cycle, swinging between solar minimum and solar maximum. During maximum, sunspots pepper its face like freckles, and flares burst outward with dramatic flare. During minimum, it calms down, smooth and deceptively serene. Yet some recent cycles have shown unusual spikes and dips, enough to raise scientific eyebrows, though not enough to trigger apocalypse sirens. Historians still argue whether these variations are entirely natural fluctuations or hints of deeper galactic influences. And that's where the unease begins. Because the sun does not exist in isolation. It is not a lone lighthouse in a static sea. It is traveling, sprinting really, around the center of the Milky Way at roughly 828,000 kilometers per hour. You're on that ride too, by the way. No seatbelt provided. As you watch, a prominence erupts from the solar limb, arching elegantly before collapsing back. It looks almost graceful, like a slow-motion ballet dancer made of fire. But beneath that beauty lies magnetic chaos. The sun's magnetic field twists and tangles due to differential rotation. The equator spins faster than the poles. Imagine trying to twist a rubber band around a spinning basketball. Eventually something snaps. On the sun, that snap is a solar flare. Here's a quirky tidbit. In the 19th century, before scientists understood nuclear fusion, some proposed that the sun was powered by gravitational contraction, basically slowly shrinking and releasing heat. Lord Kelvin himself calculated that this would only allow the sun to shine for about 20 million years. Which was awkward because geologists already suspected Earth was much older. Oops. Turns out fusion was the missing piece. Science, constantly correcting itself since forever. Shoni, you notice dark patches, sunspots. Cooler regions only about 4,000 degrees Celsius. Cooler is relative, of course. You would still be instantly converted into a poetic memory. Sunspots are signs of intense magnetic activity, and when they multiply, solar storms follow. Satellites can glitch. Radio signals can fade. Power grids can tremble. In 1859, the Carrington event sent telegraph systems sparking across continents. Operators reportedly received electric shocks, and some telegraph lines functioned even after being disconnected from power sources. It was the Victorian era's version of, have you tried turning it off and on again? And yet, for all this fury, the sun is stable. Remarkably so. It has been shining for about 4.6 billion years. That's not speculation. A radiometric dating of meteorites confirms the age of the solar system with impressive precision. The sun sits comfortably in what astronomers call hydrostatic equilibrium, the inward pull of gravity perfectly balanced by the outward pressure of fusion, a cosmic stalemate. So what could possibly push it to its limits? You drift slightly farther out now, seeing the faint halo of the heliosphere, the vast bubble carved by solar wind into interstellar space. It's the sun's personal force field, shielding you from many high-energy cosmic rays. But beyond that bubble lies the galaxy. Gas clouds, dark matter, passing stars, invisible tides of gravity stretching across light years. The sun moves up and down through the Milky Way's galactic plane in a slow oscillation that takes tens of millions of years. Well, some scientists have speculated that as it plunges through denser regions of the galaxy, gravitational forces or interstellar clouds might subtly influence solar behavior. The evidence is still debated. Historians still argue whether correlations between galactic motion and extinction events on Earth are meaningful or merely coincidental. Patterns are seductive. The universe does not promise they're causal. And here you are, suspended in that quiet, watching a star that seems eternal yet is subtly, perpetually under pressure. From its own gravity, from magnetic tension, from the galaxy's invisible tides. It doesn't look like it's struggling, it looks magnificent. But engines can hum louder before they overheat. Systems can wobble before they stabilize. The question isn't whether the sun will die. It will in about 5 billion years, swelling into a red giant. The question is whether something out there, something vast and unseen, is nudging it now, ever so slightly, toward instability. You linger, feeling the faint tremor of solar wind brush past you like warm breath. The sun flares again, brilliant and unapologetic. Not doomed, not yet, just restless. And as you drift alongside this blazing sphere, you can't help but sense that tonight's journey is only beginning, that somewhere beyond the edge of its glowing shield, something is pushing back. You remain suspended in the sun's glare, letting your eyes adjust to the constant brilliance. If it felt restless before, now you begin to understand that what you're sensing might simply be its normal rhythm, the steady breathing of a star in midlife. Because for all the drama of flares and magnetic tantrums, the sun is, one by stellar standards, astonishingly well-behaved. You drift inward in imagination, slipping past the photosphere, descending through layers you cannot physically enter, but can calmly observe in your mind. First comes the convection zone, where hot plasma rises and cooler plasma sinks in vast rolling currents. It's like a pot of soup simmering gently. If that soup were 200,000 kilometers deep and capable of erasing planets. The churning motion transports energy outward, and it's responsible for the granulated texture you see on the surface. Below that lies the radiative zone. Here, energy moves not by churning motion, but by radiation. Photons bouncing endlessly in a dense crowd of charged particles. A single photon produced in the core can take thousands, even hundreds of thousands of years to zigzag its way outward. Imagine trying to leave a packed concert where everyone is also made of light and mildly panicked. That's the radiative zone. And then, at the very center, the core. The pressure here is about 250 billion times Earth's atmospheric pressure. The temperature reaches roughly 15 million degrees Celsius. Under these conditions, hydrogen nuclei overcome their mutual repulsion and fuse into helium. This process, proton-proton chain fusion, is the mainstream mechanism that powers stars like ours. 4 hydrogen nuclei become 1 helium nucleus, and a tiny bit of mass is converted into pure energy. That energy is what keeps gravity from crushing the sun inward. Hydrostatic equilibrium, a balance so precise it's almost poetic. Yet balance does not mean stillness. You recall that the sun spins, but not like a solid ball. Its equator rotates roughly every 25 days, while its poles take about 35 days. This differential rotation twists magnetic field lines into loops and knots. Over time, the tension builds. Magnetic field lines snap and reconnect in explosive events, solar flares and coronal mass ejections. These are not signs of a star failing. They are signs of a star alive with magnetism. The 11-year solar cycle tracks the waxing and waning of this magnetic activity. At solar minimum, sunspots are scarce. At solar maximum, they multiply dramatically. This pattern has been observed since the early 17th century, when Galileo and other astronomers first sketched sunspots through primitive telescopes. Yes, Galileo, the same man who got into trouble for suggesting Earth moves around the sun, also noticed that the sun itself had blemishes. Even stars have bad skin days. But here's where it gets intriguing. The solar cycle is not perfectly regular. Some cycles are stronger, some weaker. Between 1645 and 1715, the sun entered what is known as the Maunder minimum, a prolonged period with very few sunspots. This coincided with the coldest part of the Little Ice Age in Europe and North America. Rivers like the Thames reportedly froze over during winter festivals. Historians still argue whether the reduced solar activity significantly contributed to the cooling, or whether volcanic eruptions and ocean circulation played larger roles. Climate is complicated. The sun does not sign simple contracts. You glide back toward the surface, noticing bright, active regions pulsing with energy. Modern satellites, like NASA's Solar Dynamics Observatory, monitor these areas constantly, now capturing high-resolution images in multiple wavelengths. We now track the sun's magnetic mood swings with remarkable precision, and yet, despite all this data, predictions remain imperfect. Solar Cycle 24, for instance, turned out weaker than many models forecasted. Solar Cycle 25 appears to be ramping up faster than expected. Not catastrophic, just slightly surprising. There's a quirky hypothesis you might enjoy. Some researchers have speculated that planetary alignments, particularly involving Jupiter and Saturn, might subtly influence the solar cycle through gravitational or tidal forces. It's a fringe idea and far from mainstream acceptance, but it's been explored in various models. The gravitational pull of Jupiter on the sun is real, measurable even. Whether it meaningfully alters magnetic behavior is another question entirely. Most solar physicists remain skeptical, gently raising an eyebrow. Still, the fact that the sun's behavior can vary at all hints at its sensitivity. It is a self-regulating nuclear reactor, yes, but also a complex magnetic dynamo. Tiny changes in internal flow patterns can ripple outward into massive flares. You begin to sense that pushing the sun to its limits may not require a cosmic villain with a giant lever. It could be the accumulation of subtle influences, internal and external, nudging a system already delicately balanced. The solar wind brushes past you again, a steady stream of charged particles flowing outward at hundreds of kilometers per second. This wind shapes the heliosphere, that vast bubble shielding the planets. Without it, cosmic radiation from deep space would batter Earth more intensely. Your DNA would not be thrilled. And here's a comforting mainstream fact. The sun is only about halfway through its stable hydrogen-burning phase. It has roughly 5 billion years left before it exhausts its core hydrogen and begins expanding into a red giant. Stellar evolution models are robust, grounded in nuclear physics, tested in laboratories and particle accelerators. The sun is not about to surprise us by detonating next Tuesday, but stability does not mean immunity. You drift outward slightly, watching as a sunspot group rotates into view. Magnetic loops shimmer above it, glowing in ultraviolet light. You can almost hear the quiet hum of plasma, like distant electrical wires vibrating in summer heat. The sun is not static. It breathes, pulses, flexes. And as you take in its layered structure, from core to corona, you realize something subtle. Every process inside this star depends on balance. Gravity versus fusion, rotation versus magnetic tension, outward radiation versus inward collapse. If something, anything, were to alter that balance even slightly, the effects could cascade. Not immediately, not explosively, but gradually, persistently. You hover there, calm and contemplative, watching the steady burn of hydrogen into helium. The sun does what it has always done, yet the galaxy is not empty. Forces move in the dark beyond the heliosphere. Invisible matter drifts. Stars pass. Clouds gather. For now, the engine hums smoothly, but you can't shake the feeling that the hum has a faint vibration in it, like a machine aware of distant footsteps. And you continue drifting. I'd ready to look more closely at those strange spikes in activity that have made astronomers lean just a little closer to their screens. You watch the sun rotate, slow and deliberate, like a grand clockwork sphere keeping time in fire. Days pass in minutes from your vantage point, and as the surface turns, clusters of dark sunspots drift into view. Some small and shy, others sprawling and complex, like ink spilled across molten gold. These are not random freckles, they are symptoms. Sunspots mark regions where magnetic fields punch through the photosphere, suppressing convection and cooling the surface slightly. Slightly meaning a mere 1,500 degrees Celsius, cooler than surrounding plasma. Yes, cool is doing heroic work in that sentence. When Galileo first recorded them in 1610, he helped overturn the ancient belief that celestial bodies were perfect and unchanging. Turns out even stars have wrinkles. You notice something else now. Some cycles produce modest sunspot counts, while others surge dramatically. Solar cycle 19, peaking in 1957 to 1958, was the most intense on record since systematic measurements began. Radio communications crackled. Auroras flared unusually far from the poles. It was a reminder that when the sun flexes, Earth notices. More recently, solar cycle 24, which peaked around 2014, was comparatively weak, the weakest in over a century. Then solar cycle 25 began climbing faster than many predictions anticipated. Not wildly out of control, not apocalyptic, just off-script enough to make solar physicists raise an eyebrow and refill their coffee. Historians still argue whether these irregularities are simply part of long-term magnetic variability or hints of deeper, poorly understood cycles layered atop the familiar 11-year rhythm. Some researchers propose a 22-year magnetic polarity cycle, the Hale cycle, where the sun's magnetic poles flip and then flip back. Others explore even longer periodicities, like the Gleisberg cycle, spanning roughly 80 to 100 years. The sun, it seems, has more rhythms than a jazz drummer who refuses to count to 4. You drift closer to an active region bristling with magnetic loops. The loops shimmer in ultraviolet light, arching high above the surface before reconnecting in sudden bursts. A flare erupts, a flash of X-rays and ultraviolet radiation traveling at light speed. 8 minutes later, Earth will feel the whisper of it in its upper atmosphere. Solar flares are classified by strength, A, B, C, M, and X, with X-class being the most powerful. In 2003, during what became known as the Halloween storms, an X-45 class flare erupted, the strongest ever recorded. It was so intense that it overloaded detectors, meaning it may have been even more powerful than measured. Satellites malfunctioned. Astronauts took shelter. Airlines rerouted polar flights. It was not the end of civilization, but it was a stern reminder that our star can still throw cosmic tantrums. And then there are coronal mass ejections, vast clouds of magnetized plasma hurled into space. If one is aimed directly at Earth, it can compress our magnetosphere and trigger geomagnetic storms. The 1859 Carrington event remains the gold standard of solar mischief. Telegraph lines sparked. Auroras were seen as far south as the Caribbean. Some miners reportedly woke up in the middle of the night, thinking the sun had risen early. Surprise! It was just your local star flexing across 150 million kilometers. You pause and consider the pattern. Spikes, lulls, surges of energy that sometimes exceed forecasts. Could something external amplify these peaks? There's a fringe but intriguing line of research suggesting that variations in cosmic ray flux, high-energy particles from outside the solar system, might subtly interact with the sun's magnetic field. The mainstream consensus holds that the sun's magnetic dynamo is driven primarily by internal plasma flows, But some models explore whether the heliosphere's changing environment could influence solar behavior indirectly. The evidence remains tentative. Correlation does not equal causation, as every cautious scientist will gently chant like a bedtime mantra. Still, you can't ignore that the sun moves through the galaxy, encountering regions of varying density. Interstellar space is not empty. It contains thin gas, dust, and magnetic fields. If the solar system drifts into a denser interstellar cloud, the pressure on the heliosphere could increase, compressing it. A compressed heliosphere allows more galactic cosmic rays to penetrate inward. And cosmic rays, in theory, could influence plasma behavior in subtle ways. It's speculative, but it's fascinating. You circle an especially tangled sunspot cluster, noticing how the magnetic field lines twist like overstretched rubber bands. When they reconnect, they release immense energy in seconds, equivalent to billions of hydrogen bombs. Fortunately, space is very big, and you are currently imaginary. Here's a quirky tidbit for you. Some researchers once explored whether planetary tidal forces, especially from Jupiter, could synchronize with solar cycles. The gravitational tug of Jupiter does cause the sun to wobble slightly around the solar system's center of mass, but the force is tiny compared to the violent convection within the sun. Most astrophysicists remain unconvinced that planets meaningfully drive solar spikes. Still, the idea persists in the margins, like a persistent conspiracy theorist at a physics conference. You drift outward, watching the solar wind accelerate away from the corona at up to 800 kilometers per second. During periods of heightened activity, this wind intensifies. Earth's magnetosphere shields us, but not perfectly. Satellites endure increased drag as Earth's upper atmosphere heats and expands. Power grids brace for geomagnetic currents. The spikes are real. The unpredictability is measurable. The consequences are tangible. And yet the sun remains within expected stellar behavior. It is not breaking the laws of physics. It is not swelling ominously. It is simply dynamic. But dynamic systems can resonate. They can amplify oscillations under the right conditions. Think of a playground swing. Push at just the right rhythm, and the motion grows. Push offbeat, and it dampens. The question lingering in the quiet vacuum around you is this: is something out there pushing at just the right rhythm? Historians still argue whether long-term solar variability aligns meaningfully with Earth's mass extinctions or climate shifts. Some studies suggest periodicity, the others dismantle it. Data stretches back only so far with precision. The deeper past is reconstructed from proxies, tree rings, ice cores, isotopes trapped in ancient layers. You watch another flare bloom, bright and brief. The sun is not screaming, it is not collapsing, but it is capable of surging beyond expectations. And as its magnetic heart beats in complex rhythms, you begin to wonder whether those rhythms are entirely self-composed, or whether the galaxy hums faintly in accompaniment. The spikes are small deviations in cosmic terms, yet even small deviations, given time, can accumulate. You remain suspended in the glow, listening to the steady crackle of plasma, feeling the faint tremor of a star that might, just might, be dancing to more than one tune. You ease closer to the sun's surface again, and not to be incinerated, let's keep this a metaphorical field trip, but to trace the invisible architecture that truly runs the show. Because beneath every flare, every spike, every restless shimmer, there is magnetism. Not the cute fridge magnet kind, the kind that can twist a star into knots. You hover above a sprawling, active region where dark sunspots cluster like storm cells. If you could see magnetic field lines directly, they would rise in luminous arcs, loop high into the corona, then dive back into the surface. In reality, scientists map them using spectroscopy and polarization measurements, decoding how light splits in magnetic fields. It's subtle work, like reading fingerprints left in sunlight. The mainstream fact is this: the sun operates as a magnetic dynamo. Its internal plasma flows, combined with rotation, to generate electric currents. Those currents produce magnetic fields. Because the sun's equator rotates faster than its poles, a phenomenon confirmed through helioseismology, the magnetic field lines become stretched and wound over time. Picture twisting a rubber band around a spinning watermelon. Eventually, tension builds to a snapping point. When magnetic reconnection occurs, field lines breaking and rejoining in new configurations, it releases colossal energy. This is the engine behind solar flares and coronal mass ejections. The physics of reconnection isn't unique to the Sun, it also happens in Earth's magnetosphere. But on the Sun, the scale is absurd. Energy equivalent to billions of megatons of TNT can be unleashed in minutes. And yet, from 150 million kilometers away, you mostly just see a pretty aurora and maybe lose your GPS signal for a bit. You drift into the corona, the Sun's outer atmosphere, which is paradoxically hotter than the surface, reaching millions of degrees Celsius. This coronal heating problem has puzzled scientists for decades. How can the outer atmosphere be hotter than the layer below it? One leading theory involves countless tiny reconnection events called nanoflares, small but frequent bursts that collectively maintain the corona's high temperature. Historians still argue whether nanoflares alone explain the heating or whether wave-based mechanisms, Alf-Venn waves rippling along magnetic field lines, play a dominant role. Even now, the debate hums in research journals. The corona stretches far into space, thinning gradually into the solar wind. During eclipses, you can glimpse it as a pearly halo around the darkened sun. Ancient civilizations often interpreted eclipses as omens. In reality, they were brief windows into the sun's magnetic crown. Less prophecy, more plasma physics. You circle a magnetic loop towering tens of thousands of kilometers high. Plasma flows along it like glowing syrup, tracing invisible rails. These loops can remain stable for days, or destabilize suddenly. The instability often depends on how twisted the magnetic fields become. There's a threshold, a tipping point. When magnetic helicity, the measure of twist, exceeds a certain limit, eruptions become more likely. It's here that the idea of pushing the sun to its limits starts to feel tangible. The sun is constantly building and releasing magnetic stress. Most of the time, the buildup is gradual and the release controlled. But complex systems sometimes experience cascading effects. A slightly stronger differential rotation, a subtle shift in convection patterns, a minor perturbation amplified over months. And what could cause such perturbations? Internally, changes in plasma flow patterns, like torsional oscillations, can alter magnetic field generation. These have been observed through helioseismic measurements, where scientists study sound waves traveling through the sun's interior. Yes, the sun rings like a bell, vibrating with acoustic waves. We listen by detecting tiny Doppler shifts in its surface. It's stellar ultrasound. No copay required. But externally, that's where things grow speculative. There's a quirky fringe hypothesis suggesting that dark matter particles passing through the sun might accumulate in its core, subtly affecting energy transport. The mainstream view holds that dark matter interactions are far too weak to meaningfully alter solar behavior at present densities. Still, physicists model such scenarios because ruling things out is part of the fun. If dark matter did cluster in sufficient amounts, it could, in theory, influence core temperature gradients. For now, evidence says unlikely, but not impossible in principle. You glide along a current sheet in the corona, a thin boundary separating regions of opposite magnetic polarity. The heliospheric current sheet extends outward through the solar system like a wavy skirt spinning in space. As the sun rotates, this sheet spirals into a shape known as the Parker spiral. It's beautiful in diagrams. Slightly less beautiful if you're a spacecraft flying through charged particle turbulence. The Parker Solar Probe, launched in 2018, has flown closer to the sun than any previous mission. It has dipped into the corona itself, sampling plasma and magnetic fields directly. One of its discoveries includes switchbacks, sudden reversals in magnetic field direction within the solar wind. These were more common than expected, not alarming but surprising. The sun once again showing that it keeps a few tricks up its sleeve. Historians still argue whether such switchbacks originate near the surface from magnetic funnels or emerge from turbulence farther out. The source matters because it tells us how energy and momentum transfer outward. It tells us how stable, or unstable, the magnetic engine truly is. You pause, letting the scene slow. Magnetic loops glow softly. Plasma flows. Reconnection events flicker like distant lightning. Nothing looks catastrophic. In fact, it looks rhythmic, predictable in its unpredictability. But magnetic systems can resonate. If external gravitational tides, galactic magnetic fields, or interstellar pressure subtly alter boundary conditions at the heliosphere's edge, the feedback could propagate inward over time. Not dramatically, not instantly, but gradually. Imagine tightening a violin string ever so slightly. The instrument still plays, but the pitch shifts. The tone changes. The harmonics respond. The sun is an instrument strung across gravity and fusion. Its magnetic heart beats in layered cycles. And while its core burns steadily, where its outer layers remain sensitive to flow patterns and rotational shear. You drift outward once more, watching the corona stream into space, luminous and fragile looking despite its violence. The magnetic heart beneath it continues to wind and unwind, building tension, releasing it, building again. For now, the rhythm holds, but you can feel how finely tuned it is, how a star this powerful can still depend on delicate balances between twist and release. And somewhere beyond the shimmering loops and snapping field lines, beyond the glowing boundary of the heliosphere, the galaxy waits, pressing gently, persistently on the outermost strings of this magnetic instrument. You drift outward, beyond the last luminous arcs of the corona, past the steady stream of solar wind particles racing away from the sun like an endless exhale. The light softens here. The roar becomes a whisper, and for the first time you begin to look not at the sun itself, but at what approaches it, because space is not empty. It only pretends to be. Ahead of you lies interstellar space, filled with tenuous gas, mostly hydrogen, along with traces of helium and microscopic dust grains forged in ancient supernovae. The density is astonishingly low by earthly standards, sometimes just a few atoms per cubic centimeter. But over astronomical distances, even thin fog can matter. The sun, as it orbits the center of the Milky Way, moves through different regions of this galactic medium. Right now, it resides inside what's called the local interstellar cloud, a region of slightly denser gas about 30 light-years across. This is a mainstream, on a well-mapped fact confirmed by observations from spacecraft like Voyager and IBEX. The solar system entered this cloud tens of thousands of years ago. You imagine the sun like a ship cutting through cosmic mist. Its solar wind pushes outward, carving a protective bubble called the heliosphere. That bubble acts as a shield, deflecting many high-energy galactic cosmic rays. But the size and shape of the heliosphere depend on external pressure from interstellar gas and magnetic fields. If the sun drifts into a denser cloud, one with higher particle density, the external pressure increases. The heliosphere could compress, shrinking inward. Think of squeezing a stress ball. The more pressure applied from outside, the smaller the protective bubble becomes. And that compression has consequences. Voyager 1 and Voyager 2, launched in 1977, might have now crossed the heliopause, the boundary where solar wind gives way to interstellar space. Their instruments detected changes in particle density and magnetic field orientation, confirming that this boundary is dynamic, not fixed. It fluctuates depending on solar activity and external conditions. It breathes. Historians still argue whether past passages through denser interstellar clouds significantly altered Earth's climate or cosmic ray exposure. Some geological evidence suggests periodic increases in certain isotopes, like iron-60, deposited by nearby supernova millions of years ago. Whether those events directly impacted solar behavior remains debated. You glide along the outer edge of the heliosphere. It's not a perfect sphere, but more like a comet-shaped bubble, and with a rounded nose facing the direction of solar motion and a trailing tail stretching behind. The interstellar medium presses against it constantly, not violently, just persistently. Here's where things become intriguing. If the heliosphere shrinks, more galactic cosmic rays can penetrate deeper into the solar system. Cosmic rays are high-energy particles, often originating from distant supernova explosions. When they collide with atoms in Earth's atmosphere, they produce cascades of secondary particles. They also leave chemical fingerprints in ice cores and tree rings. Carbon-14 spikes that scientists use to reconstruct past solar activity. But what about their effect on the sun itself? Mainstream astrophysics suggests that the sun's core fusion processes are largely insulated from such external influences. Or the outer layers might respond to changing boundary conditions, but the core remains governed by immense internal pressure and temperature. Still, plasma physics is notoriously complex. Small perturbations in magnetic boundary conditions can ripple inward through feedback loops. Some fringe models propose that enhanced cosmic ray flux could influence magnetic reconnection rates in the corona. The evidence is limited, the mechanisms speculative, but the idea persists in academic corners, that the galaxy's environment may subtly modulate solar magnetism over long timescales. You drift farther into interstellar space, looking back at the sun. It appears smaller now, a brilliant star wrapped in a faint bubble. The galaxy surrounds it, spiral arms filled with molecular clouds, star-forming regions, remnants of exploded giants. Either about 2.6 million years ago, a star called Schultz's star passed within roughly 0.8 light-years of the sun. That's close in cosmic terms, well within the outer Oort cloud of icy bodies. Mainstream calculations confirm this flyby. It likely disturbed some comets, nudging them inward over millions of years. A reminder that the sun is not isolated. Stars wander. Imagine a future close encounter with a dense interstellar cloud. The heliosphere compresses dramatically. Cosmic ray flux increases. Earth's atmosphere experiences enhanced ionization. Satellites face greater radiation exposure. And perhaps, just perhaps, the sun's outer magnetic layers feel the squeeze. Not a shove, not a punch. A squeeze. There's a quirky historical note here. In the early 20th century, some scientists speculated that passing through interstellar clouds could dim the sun significantly by absorbing light. We now know the densities are far too low for that. No galactic smog apocalypse is looming, but the concept that our star moves through changing environments remains valid. You hover at the boundary, watching charged particles collide and deflect. The heliopause ripples like the skin of a soap bubble under gentle breath. It is both shield and interface. The sun continues to emit solar wind steadily, but you sense how its protective bubble depends on equilibrium between internal output and external pressure. If solar wind weakens during a prolonged solar minimum, like the Maunder minimum, the heliosphere contracts even without denser surroundings. Combine that with a denser interstellar region, and the compression could be more pronounced. Historians still argue whether such combined effects occurred in Earth's distant past, and whether they correlate with extinction events or climatic anomalies. The data is tantalizing, but incomplete. You turn back toward the sun, glowing steadily within its shimmering boundary. It does not look threatened. It does not look strained. But you now understand something subtle. Even a star is embedded in a larger ecosystem. Its limits are not defined solely by its core, but also by its surroundings. The galaxy is not passive. It exerts pressure, gravitational, magnetic, particulate. And as the sun sails forward on its 225 million year orbit around the Milky Way, it cannot help but encounter whatever lies ahead. For now, the interstellar medium presses gently against its bubble, like a tide against a ship's hull, gentle but constant. You drift even farther out now, zooming beyond the immediate mist of the local interstellar cloud, widening your view until the sun is just one bright bead in a vast spiral tapestry. From here, the scale changes everything. The sun is not merely moving through thin gas. It is orbiting the gravitational heart of an entire galaxy. The Milky Way contains an estimated 100 to 400 billion stars. That's not a typo. Astronomers genuinely debate the number. Counting stars in a galaxy is a bit like trying to count fireflies in a fog bank while riding a carousel. You get an estimate, then you argue about it at conferences. Our sun sits roughly 26,000 light-years from the galactic center, orbiting that dense region once every 225 to 250 million years. One full galactic year ago, we dinosaurs were just getting comfortable. The sun, meanwhile, keeps cruising at about 828,000 kilometers per hour, held in place by the Milky Way's combined gravity, visible stars, gas, dust, and a large invisible component known as dark matter. You float above the galactic disk and see it clearly, a flattened spiral with sweeping arms. The sun does not move in a perfect flat circle. Instead, it oscillates up and down through the galactic plane, bobbing like a cork on a cosmic ocean. One full vertical oscillation takes roughly 60 to 70 million years. And here's where the pressure becomes more abstract. When the sun passes through the denser midplane of the galaxy, gravitational tides are slightly stronger. The density of gas, dust, and possibly dark matter increases. To the Oort cloud, a distant spherical shell of icy bodies surrounding the solar system, may feel these tidal forces most strongly. Comets can be nudged inward, increasing the likelihood of impacts in the inner solar system. Mainstream astrophysics supports this galactic tide effect on the Oort cloud. It's subtle but measurable in models. Whether these oscillations correlate with periodic mass extinctions on Earth is another matter. Historians still argue whether a roughly 26 to 30 million year extinction pattern in the fossil record reflects galactic plane crossing or a statistical coincidence. The debate has seesawed for decades, like a metronome that refuses to settle. But you're not just thinking about comets now. You're thinking about the sun itself. Gravity from the galaxy acts on the entire solar system, including the sun's outer layers. The tidal forces at our distance from the galactic center are extremely weak compared to the sun's own gravity. If you compare them directly, the sun's self-gravity utterly dominates. It's like comparing a firm handshake to the gravitational influence of a polite nod from across a football field. And yet, tides accumulate over time. On Earth, ocean tides are caused by the moon's gravity, even though the moon's pull is far weaker than Earth's gravity. It's the differential, the slight difference in gravitational pull across a body, that matters. The Milky Way exerts tidal forces across the solar system. They are tiny, yes, but the sun's magnetic outer layers are dynamic, fluid, and sensitive to motion. Some researchers have explored whether galactic tides might influence angular momentum distribution in the outer solar system, and indirectly affecting the sun's barycentric motion, the wobble caused by planetary gravitation. It's a chain of subtlety. Galaxy influences solar system. Solar system influences solar spin dynamics. Solar spin influences magnetic field generation. Is the effect significant? Most models say it's minimal, but minimal is not zero. You drift closer to the galactic center in your mind's eye. There, Sagittarius A star, a supermassive black hole 4 million times the mass of the sun, anchors the galaxy. Don't worry, it's far too distant to have any dramatic effect on our star beyond its role in shaping galactic orbits. Still, it's comforting to know there's a gravitational heavyweight keeping the spiral organized. Every neighborhood needs a strong HOA president, apparently. And the spiral arms themselves are regions of enhanced density, star-forming zones rich in gas and dust. The sun passes through these arms periodically over hundreds of millions of years. During those passages, the local stellar density increases. More nearby stars, more supernovae, more gravitational perturbations. Some studies suggest that supernova frequency may rise when the solar system traverses a spiral arm. Supernovae can bathe nearby space in cosmic rays. Geological records on Earth show traces of iron-60 isotopes consistent with at least one nearby supernova about 2 to 3 million years ago. That's not fringe. That's measured in ocean crust samples. Did such events push the sun toward instability? Almost certainly not directly. But increased cosmic ray pressure and interstellar density could compress the heliosphere further during such epochs. You hover above the galactic plane and imagine the sun plunging through it. Gas density increases slightly. Magnetic fields strengthen. Dark matter density, whatever it truly is, may peak near the midplane. Here's a quirky fringe idea. Some physicists have speculated that if dark matter consists of weakly interacting massive particles, they could accumulate in stellar cores more efficiently during higher density crossings. Accumulated dark matter might alter heat transport inside stars. Most evidence suggests that for sun-like stars in our galactic neighborhood, this effect would be vanishingly small, but the equations are explored nonetheless. The universe invites curiosity. Historians still argue whether dark matter density variations across the galactic disk meaningfully influence stellar evolution on small scales. Current consensus leans toward probably negligible for our sun, but research continues. You turn back toward our star. From this vantage, it looks serene, a stable yellow dot among billions, and yet it rides invisible tides. It oscillates through density gradients. It exists within a gravitational web woven by the Milky Way. The phrase pushing the sun to its limits begins to feel less like a single dramatic shove and more like a lifetime of gentle pressures. Galactic tides, spiral arm crossings, interstellar density fluctuations, cosmic ray flux changes. None of these alone can overwhelm a 1.989 times 10 to the power of 30 kilogram sphere powered by nuclear fusion. But together, they form the environment in which the sun lives. You drift slowly downward again, back toward the heliosphere, carrying with you a new perspective. The sun is not merely a self-contained furnace. It is a citizen of a galaxy, a traveler on a long orbital path through changing gravitational terrain. And as it continues its quiet, 225 million year journey around the Milky Way, the tides of the galaxy keep brushing against it, softly. You linger at the edge of the heliosphere, where sunlight thins and the galaxy's darkness presses closer, and you begin to consider something stranger still, something you cannot see, cannot touch, and yet which outweighs all the visible stars combined. Dark matter. You don't see it swirling in elegant arcs. You don't watch it sparkle. It doesn't glow, absorb, or reflect light. And yet, without it, galaxies like the Milky Way would spin themselves apart. That's the mainstream fact anchoring this mystery. When astronomers measure how fast stars orbit galactic centers, they move too quickly for visible matter alone to hold them in place. The extra gravity must come from something unseen. So here you are, imagining the sun moving not only through gas and dust, but through a vast halo of dark matter enveloping the galaxy. A halo that outweighs all luminous matter by roughly 5 to 1. You float in this invisible sea and ask the quiet question, could this unseen mass be pushing on the sun? On large scales, absolutely. Dark matter shapes the gravitational field of the Milky Way. It determines the sun's orbital speed around the galactic center. Without it, your star would follow a very different path. So in that sense, dark matter already exerts influence, constant, structural, undeniable. But could it do more? Some physicists have explored whether dark matter particles, if they are weakly interacting massive particles, or WIMPs, could pass through the sun and occasionally collide with atomic nuclei. Over billions of years, a small fraction might lose enough energy to become gravitationally trapped inside the sun's core. There, they could accumulate. The idea isn't science fiction. It's been modeled in peer-reviewed research. If enough dark matter gathered in the core, it might transport heat differently than ordinary plasma. It could, in theory, slightly alter temperature gradients and fusion rates. However, and this is important, current estimates of local dark matter density suggest the effect would be extraordinarily small for a star like the Sun. Observations of solar neutrinos and heliosismology match standard solar models very well. There's no clear sign that dark matter is significantly modifying the Sun's internal engine. Still, historians still argue whether more exotic forms of dark matter, self-interacting particles, ultralight fields, or even primordial black holes, could produce subtle stellar effects not yet fully ruled out. The debate is ongoing, and the equations are, let's just say they are not bedtime reading unless you truly enjoy integrals. You drift inward in imagination, toward the core again. Fusion proceeds steadily. Hydrogen nuclei merge through the proton-proton chain. Neutrinos stream outward, detected on Earth in underground observatories like Super Kamiokande and the Sudbury Neutrino Observatory. Those detections confirm that our understanding of solar fusion is remarkably accurate. The solar neutrino problem of the 20th century, when fewer neutrinos were detected than expected, was eventually resolved by discovering that neutrinos oscillate between types. Physics corrected itself, like it always does, albeit sometimes dramatically. If dark matter were dramatically altering fusion rates, neutrino flux would likely reveal discrepancies. So far, it hasn't. But you're not done wondering. Dark matter density is not perfectly uniform throughout the galaxy. It may be slightly denser near the galactic plane. As the sun oscillates up and down through the disk, it could pass through regions of marginally higher dark matter concentration. The change would be small, but persistent over millions of years. And imagine walking through a faint mist. You barely notice it, but walk long enough and your hair grows damp. There's a fringe but fascinating hypothesis suggesting that if dark matter consists of certain exotic particles, like axions, they might convert into photons in strong magnetic fields. The sun's magnetic field is certainly strong. Experiments like the CERN Axion Solar Telescope have attempted to detect such processes. So far, results remain inconclusive. The search continues. You pause near a twisting magnetic loop and imagine invisible particles passing straight through it, unaffected by plasma turbulence. Dark matter barely interacts with normal matter. Trillions of hypothetical particles could stream through your body right now without a whisper. It's the universe's ultimate introvert, yet its gravity shapes everything. As you widen your view again to the galactic scale, the sun's orbit is determined largely by the gravitational potential created by dark matter. If that distribution changed, say if the sun passed through a clump or subhalo, the gravitational environment would shift slightly. Could such a shift alter the solar system's angular momentum enough to affect the sun's barycentric wobble? Possibly in theory. In practice, most models predict such effects would be minuscule compared to planetary gravitational influences. Still, the concept lingers. The sun is embedded in an invisible framework. You consider another idea, more speculative still. What if dark matter occasionally forms dense streams or filaments, leftovers from smaller galaxies absorbed by the Milky Way? Some simulations predict such substructures. If the solar system crossed one, local dark matter density could spike temporarily. Would the sun notice? Probably not in any dramatic way. But plasma systems are nonlinear. Small perturbations can sometimes produce amplified responses under the right conditions. Solar magnetic fields, in particular, are sensitive to flow dynamics. Historians still argue whether any observed periodicities in solar behavior align with predicted dark matter density variations. The data is far from conclusive. Most astrophysicists remain cautious, favoring internal magnetic dynamo explanations over exotic external drivers. You drift back toward the sun, watching it glow steadily against the star-filled backdrop. It doesn't flicker in response to invisible halos. It doesn't shudder under unseen tides, and yet it moves within them. Dark matter doesn't shove the sun like a cosmic bully. It shapes the stage on which the sun performs. It defines the gravitational bowl in which our star rolls, the curvature of space-time guiding its path. Perhaps pushing the sun to its limits is not about a single, because while dark matter is subtle and diffuse, stars can be blunt instruments, massive, wandering, occasionally impolite. The sun is not anchored to a fixed neighborhood. It moves through the Milky Way alongside countless other stars, each following its own orbit around the galactic center. Over millions of years, these paths occasionally bring stars relatively close to one another. Not close enough for Hollywood-style collisions, space is far too spacious for that, but close enough for gravity to whisper. About 2.6 million years ago, a small red dwarf system known as Schultz's star passed within roughly 0.8 light-years of the sun. That's less than a light-year. Well inside the outer Oort cloud, the vast spherical shell of icy bodies extending perhaps 50,000 to 100,000 astronomical units from the sun. This flyby is not speculative. Why? It's supported by precise measurements of stellar motion from surveys like Gaia. You imagine it now, a dim red star gliding silently through the outskirts of our solar system, barely noticeable against the stellar backdrop. From Earth, it would have appeared as just another faint star, but gravitationally it may have stirred the Oort cloud, nudging comets onto slow inward trajectories. Not a shove, a nudge. Over millions of years, some of those perturbed comets could enter the inner solar system. Increased cometary impacts might influence planetary environments. On Earth, impacts have shaped history before. Just ask the dinosaurs. Though to be fair, they're not currently accepting interview requests. Historians still argue whether periodic increases in impact rates correlate with cycles of stellar flybys or galactic plane crossings. Some studies suggest weak periodic patterns. Others find none statistically robust. The fossil record is messy. Gravity is patient. But what about the sun itself? When a star passes within a light year or less, its gravitational pull on the sun is extremely small compared to the sun's own gravity. The primary effect is on loosely bound objects in the outer solar system, not on the dense, fusion-powered core of the sun. Direct stellar flybys are unlikely to significantly disturb the sun's internal processes. Still, imagine a closer encounter. Simulations suggest that over billions of years, stars occasionally pass within zero point 0.1 to zero point 0.2 light years. Rare, but not impossible. A close enough flyby could gravitationally disturb not just the Oort cloud, but the outer planetary orbit slightly. The sun would wobble in response, while adjusting its motion around the solar system's barycenter. You picture the sun as a dancer subtly shifting its balance when someone brushes past in a crowded ballroom. The shift is tiny, almost imperceptible, but measurable with modern instruments. The Gaia spacecraft has revolutionized our understanding of stellar motion. By tracking the precise positions and velocities of over 1 billion stars, astronomers can project future close encounters. One notable example is Gliese 710, a star predicted to pass within about 0.2 light-years of the Sun in roughly 1.3 million years. That's close enough to significantly disturb the Oort cloud, potentially sending a shower of comets inward. Mainstream models suggest Gliese 710 will not directly threaten the Sun's stability. It won't strip planets away. It won't ignite stellar fireworks. But it will tug at the solar system's fringes. Now consider cumulative effects. Over the Sun's 4.6 billion-year lifetime, it has likely experienced multiple close stellar flybys. Each one nudges the outer solar system. Each one slightly alters the distribution of distant icy bodies. And each one shifts the Sun's motion minutely within the galaxy. Could repeated gravitational nudges influence the Sun's rotation over geological timescales? The effect would be extraordinarily small, but angular momentum exchange within multi-body systems can produce subtle long-term evolution. Most astrophysicists believe internal magnetic braking, where stellar winds carry away angular momentum, is the dominant factor in slowing the Sun's rotation over time. But external perturbations add complexity to the system. Here's a quirky historical aside. In the 1980s, some scientists proposed the existence of a hidden companion star to the Sun, dubbed Nemesis, that periodically disturbed the Oort cloud and triggered mass extinctions on Earth. The idea gained public fascination but lacks strong observational evidence. Extensive surveys have found no such companion star. Nemesis, it seems, was more myth than menace. Still, the fact that the idea seemed plausible for a time highlights something important. Stellar encounters are real. The Sun's environment changes. You drift outward again and imagine the galaxy as a slow-motion swarm. Stars orbit, occasionally weaving near one another. Most pass at safe distances, but gravity never truly switches off. It extends infinitely, fading with distance but never vanishing. The Sun, for all its mass, is not immune to this gravitational web. You consider how even slight changes in the Sun's galactic orbit could alter its exposure to spiral arms, supernova frequency, and interstellar density. A close stellar encounter might shift its trajectory by a fraction of a degree, insignificant in daily terms, but meaningful over tens of millions of years. Historians still argue whether certain extinction events align with predicted increases in comet flux from stellar perturbations. Some correlations have been proposed, others dismantled. Science proceeds carefully, wary of seeing patterns in cosmic noise. You turn back toward the Sun, imagining it long ago, younger and spinning faster, encountering different stellar neighbors in its birth cluster. But yes, mainstream astronomy suggests the Sun likely formed in a dense stellar cluster about 4.6 billion years ago. In those early days, close stellar encounters would have been more common. The young Sun may have experienced far stronger gravitational interactions before the cluster dispersed. Did those early encounters shape the architecture of the solar system? Almost certainly. Did they push the Sun toward instability? Probably not, but they influenced its environment profoundly. You hover in the quiet darkness between stars, recognizing that space is vast, but not static. The Sun is part of a choreography of motion, stars gliding, gravity whispering, trajectories bending ever so slightly over time. No single passing star is likely to push the sun to its limits, but over billions of years, the cumulative ballet of stellar encounters helps define the boundaries within which our star lives. And somewhere in the future, another faint red star will glide through the outskirts of the solar system, tug gently at distant comets, and continue the slow gravitational conversation that has always surrounded the sun. Soft touches, long echoes, a dance that never quite ends. You drift back inward again, leaving behind wandering red dwarfs and distant stellar near misses, and settle into a quieter, more speculative corner of cosmic history. Because sometimes the thing pushing the sun to its limits isn't a confirmed flyby or a measured halo of dark matter. Sometimes it's an idea. In the 1980s, a hypothesis emerged that captured both scientific curiosity and late-night documentary drama: the Nemesis theory. The proposal was simple, yet almost elegant. What if the sun had a distant, unseen companion star orbiting far beyond Pluto, so far out that it completed one orbit every 26 to 30 million years? Each time it swung close to the inner Oort cloud, it would gravitationally disturb comets, sending showers inward. Some of those comets would strike Earth, triggering periodic mass extinctions. The timing seemed tempting. Some paleontologists had suggested a rough 26 million year cycle in extinction events. Correlation met imagination, and Nemesis was born. You imagine it now, a dim red or brown dwarf companion, lurking tens of thousands of astronomical units away, orbiting silently in the cold dark. Too faint to easily detect with older infrared surveys. A shadow partner to our bright sun. On to mainstream fact first. Extensive sky surveys, including infrared missions like WISE, have found no evidence of such a companion within the proposed distance ranges. If Nemesis existed as originally described, we almost certainly would have detected it by now. The consensus today is that the Nemesis hypothesis is highly unlikely. Still, historians still argue whether extinction periodicities are real or artifacts of incomplete fossil data. The supposed 26 million year cycle has weakened under statistical scrutiny, though debates persist. Science, like the sun's magnetic field, sometimes loops back on itself before settling. But let's stay with the idea for a moment. If the sun did have a distant massive companion, its gravitational pull would alter the sun's barycentric motion significantly. The solar system's center of mass would shift farther from the sun's center. The sun would wobble more dramatically as both bodies orbited their shared center of gravity. That wobble is not hypothetical in general. Even without Nemesis, the sun already moves around the solar system's barycenter, due largely to Jupiter's mass. Jupiter contains more than twice the mass of all other planets combined. Its gravitational pull causes the sun to shift slightly, sometimes even moving outside its own visible surface, relative to the barycenter. Yes, technically, the sun occasionally orbits a point just outside itself. It's a humbling thought. Even stars have to compromise. Now imagine adding a distant brown dwarf companion into that gravitational equation. The sun's motion would become more complex. Over long timescales, while changes in angular momentum distribution could subtly influence internal rotational dynamics. And as you already know, rotation plays a key role in magnetic field generation. Could a hidden companion push the sun's magnetic dynamo toward instability? In theory, sustained gravitational perturbations might alter rotational shear in the outer layers. In practice, stellar interiors are dominated by immense internal forces. Most astrophysicists consider such external influences too weak to significantly disrupt fusion equilibrium or magnetic cycles. Still, the concept lingers because it connects celestial mechanics to biological history. A companion star triggering comet showers triggering extinctions, extinctions reshaping evolution. It's the kind of cosmic domino chain that makes you feel both tiny and oddly central to the story. There's another twist. Even without Nemesis, the sun was likely born in a dense stellar cluster. In those early millions of years, it probably had dozens or hundreds of nearby stellar siblings. Some may still roam the galaxy as solar siblings, sharing similar chemical compositions. A few candidates have been identified through spectral analysis, though none close enough to act as a long-term companion. In that crowded nursery, gravitational interactions would have been far stronger than anything the modern sun experiences. Protoplanetary disks could have been truncated. Outer regions stirred. The architecture of the early solar system shaped by stellar neighbors, brushing past like shoppers in an overpacked aisle. You smile at the thought. The sun, once a baby star in a busy cluster, now middle-aged and cruising through quieter galactic suburbs. And yet, even in relative solitude, it cannot escape gravitational relationships. Here's a quirky tidbit. Some alternative nemesis-like ideas suggested not a star, but a massive, undiscovered planet, sometimes dubbed Planet X, lurking far beyond Neptune. While modern searches continue for a possible Planet 9 to explain certain orbital anomalies in distant Kuiper Belt objects, any such planet would be far too small to significantly influence solar fusion or magnetic behavior. It might tweak comet trajectories, but it wouldn't stress the sun's core. Still, the search continues. Astronomers scan the sky patiently, hunting for faint moving dots against the background stars. You drift beside the sun again, watching its surface ripple and flash. It looks self-contained, self-sufficient, a nuclear engine balanced by gravity. And yet the idea of nemesis reminds you of something deeper, that we often search for external culprits when systems fluctuate, when extinction patterns appear, when solar cycles vary slightly from expectation. Historians still argue whether humanity has a tendency to overpattern, to find cycles where randomness suffices. The sun's variability may not require a shadow companion. It may simply be the natural complexity of magnetohydrodynamics at stellar scale. But speculation has value. It pushes instruments to improve, surveys to deepen, models to refine. Nemesis may not exist, but the question it posed forced astronomers to examine the solar system's outer architecture more closely, to map the sky more thoroughly, to confront how little we once knew about our own neighborhood. You float in the warm glow of starlight and consider how even disproven ideas can illuminate truth. The sun does not appear haunted by a hidden twin. No dark star circles it in a 26 million year doom loop. But the possibility once felt plausible, and that alone tells you something important. The sun's limits are not just defined by physics, but by how deeply we understand the environment it inhabits. For now, nemesis fades into myth. The sun burns alone, but never entirely untouched. You remain beside the sun, watching its surface ripple in slow, luminous currents. And now you turn your attention to something far less hypothetical than nemesis. No hidden star, no invisible twin, just two very real giants that never stop tugging. Jupiter and Saturn. You shift your perspective slightly outward and see them there. Jupiter massive and striped, Saturn elegant with its rings, circling faithfully in their distant lanes. Jupiter alone contains more than twice the mass of all the other planets combined. If the solar system were a corporate meeting, Jupiter would absolutely dominate the agenda. Here's the mainstream fact. The sun does not sit perfectly still at the center of the solar system. Instead, it moves around the system's barycenter, the true center of mass shared by all orbiting bodies. Because Jupiter is so massive, the barycenter often lies just outside the sun's visible surface. That means the sun technically wobbles as Jupiter orbits. Not dramatically, not in a way you'd notice from Earth without precise instruments, but measurably. You imagine the sun performing a complex dance step, shifting slightly this way, then that, as Jupiter completes its 11.86-year orbit. Saturn, with its 29-year orbit, adds another layer to the choreography. When Jupiter and Saturn align on the same side of the sun, their combined gravitational pull shifts the barycenter a bit more. This barycentric motion is real and calculable. Astronomers use it when searching for exoplanets around distant stars, watching for similar stellar wobbles caused by unseen planets. In fact, that's one of the primary methods used to discover thousands of exoplanets, detect the star's subtle motion. But here's where the speculation begins to shimmer. Some researchers have proposed that the sun's barycentric motion might correlate with aspects of the solar cycle. The idea is that changes in the sun's orbital angular momentum, driven by planetary alignments, could influence internal rotational dynamics, which in turn affect the magnetic dynamo. It's a delicate chain of reasoning. Planetary gravity alters solar motion. Solar motion influences internal flows. Internal flows shape magnetic cycles. Mainstream solar physics remains cautious. Most models indicate that the gravitational forces exerted by Jupiter and Saturn on the Sun are tiny compared to the immense forces inside it. The pressure in the solar core is so enormous that planetary tides seem almost trivial by comparison. And yet, tidal forces operate on differences in gravitational pull across a body, not just total force. Even small differential effects, if persistent and resonant, can accumulate over time. Think of pushing a swing gently but consistently at the right rhythm. Historians still argue whether observed correlations between planetary alignments and solar activity are statistically meaningful or coincidental. Some studies claim intriguing synchronizations. Others dismantle them under stricter analysis. The debate has lasted decades and shows no sign of politely concluding. You drift closer to the sun's equator and imagine Jupiter's gravitational pull, stretching it ever so slightly, raising solar tides measured in mere millimeters. Yes, millimeters. Compared to a star nearly 1.4 million kilometers wide. It sounds laughably small, but plasma is not rigid rock. The sun is fluid, conductive, and magnetically sensitive. Its outer layers respond to rotation, shear, and turbulence. If barycentric shifts subtly modify rotational patterns, they could, in theory, modulate magnetic field generation. Here's a quirky historical detail. In the 19th century, before the magnetic dynamo theory was fully developed, some scientists speculated that planetary alignments might directly trigger sunspots. The idea fell out of favor as internal magnetic models gained strength. But every few decades, someone revisits the planetary hypothesis with new mathematical tools. You glance outward again. Jupiter continues its steady orbit, utterly indifferent to the debate. Saturn follows, stately and patient. Together they create complex gravitational rhythms. The sun's motion around the barycenter traces looping patterns, sometimes smooth, sometimes more erratic, depending on planetary configurations. Interestingly, during certain periods in history, the sun's barycentric motion becomes more irregular, even briefly reversing direction relative to the center of mass. Some researchers have noted that such episodes coincided with prolonged solar minima, like the Maunder minimum. Coincided. That word again. So full of possibility and caution. Historians still argue whether this alignment is meaningful or a product of selective data interpretation. It's easy to spot patterns when you're looking for them. Harder to prove causation. You hover just above the photosphere as a sunspot cluster rotates into view. Magnetic loops shimmer overhead. Plasma churns below. The sun's differential rotation continues its relentless twisting of magnetic field lines. Could the gentle tug of giant planets synchronize with these internal rhythms? Most solar physicists would say the internal dynamo is self-sustaining and largely independent of planetary forcing. The energy scales simply don't compare. Yet the sun is a nonlinear system. Nonlinear systems can exhibit resonance, small periodic inputs leading to amplified responses if timing aligns. You imagine the sun as a vast bell. Strike it hard and it rings loudly. Tap it gently but rhythmically at just the right frequency, and you might still coax a noticeable tone. Are Jupiter and Saturn tapping at the right frequency? The evidence remains inconclusive. You drift outward slightly, watching the entire solar system in motion. The sun looping around the barycenter, planets orbiting in layered rhythms. It's less a static hierarchy and more a gravitational ballet. Nothing here looks violent. Nothing looks like it's pushing the sun toward collapse. But the motion is constant. The tugs never cease. The barycenter shifts day by day, year by year. Perhaps the sun's limits are not tested by singular catastrophic forces, but by endless subtle interactions. A millimeter here, a fractional rotation change there. Over millions of years, small influences weave into larger patterns. You settle into the warmth again, feeling the sun's steady fusion pulse beneath it all. Jupiter pulls. Saturn follows. The sun responds, ever so slightly. And the dance continues, measured not in steps, but in decades and centuries, in cycles and reversals, in the quiet geometry of gravity, shaping a star that still burns, still balances, still hums beneath the combined influence of everything that orbits it. You stay with that dance for a moment longer, or watching the sun trace its looping path around the solar system's barycenter. From a distance, it almost looks uncertain, like it can't quite decide where the center is. But of course, the center isn't fixed. It shifts constantly as planets move, especially the heavyweights. You widen your view until you can see the entire solar system from above. The barycenter, the true center of mass, hovers sometimes inside the sun, sometimes just outside its surface. When Jupiter sits on one side, the sun leans ever so slightly toward it. When Saturn joins in, the lean becomes a little more pronounced. Add Uranus and Neptune, and the geometry grows more intricate. Here's the solid mainstream fact. The sun's motion around the barycenter can be calculated with extreme precision using Newtonian mechanics and general relativity. And this wobble is not mysterious. It's expected. It's measurable. It's the same principle astronomers use to detect exoplanets orbiting distant stars. But when you look at the sun not as a rigid object, but as a churning sphere of plasma with layered rotation and magnetic feedback loops, the wobble begins to feel less trivial. The sun's outer layers rotate at different speeds than its inner radiative zone. Between them lies the tachocline, a thin transitional layer where rotation shifts from differential, in the convection zone, to nearly uniform, in the radiative zone. The tachocline is widely believed to play a critical role in generating the sun's magnetic field. It's like the clutch plate in a cosmic engine. Helioseismology, the study of sound waves traveling through the sun, has mapped these internal layers with astonishing accuracy. So by observing oscillations on the solar surface, scientists can infer internal flow speeds and rotation profiles. It's one of the great triumphs of modern astrophysics. We can't see inside the sun, but we can hear it, and what we hear is mostly stable, but not perfectly. Subtle variations in internal rotation have been observed over time. Torsional oscillations that migrate with the solar cycle. Bands of slightly faster and slower rotation drift across latitudes. These flows are linked to magnetic activity patterns. Historians still argue whether long-term modulations in these flows might connect to external gravitational influences, or whether they are entirely self-organized features of magnetohydrodynamics. Most evidence favors internal processes, but the door is not welded shut. So you imagine the sun's barycentric motion subtly altering its angular momentum distribution. When the sun shifts around the center of mass, its velocity relative to that point changes. Some researchers have proposed that variations in the sun's orbital angular momentum correlate with prolonged solar minima. One controversial claim suggests that during certain periods, like the Maunder minimum, the sun's motion around the barycenter became more disordered, even briefly retrograde. The timing overlaps intriguingly. But overlap is not explanation. The energy involved in barycentric motion is minuscule compared to the energy of fusion in the core. That's the counter-argument. The sun emits about 3.8 times 10 to the power of 26 watts of power continuously. Compared to that, planetary gravitational influences are whispers in a hurricane. Still, the nonlinear systems can respond to small boundary perturbations. The sun's magnetic dynamo operates near thresholds of instability. Magnetic fields build, snap, reverse. A slight change in rotational shear at the tachocline might influence how magnetic flux tubes rise to the surface. You drift closer to that imagined tachocline, that thin shearing layer deep beneath the surface. Plasma flows sideways here, stretched by rotation. Magnetic fields amplify, winding tighter. If rotation shifts even fractionally over decades, the magnetic cycle could adjust its amplitude or timing. Here's a quirky historical aside. In the 1970s, some researchers suggested that planetary alignments might synchronize solar cycles similarly to how tidal forces influence Earth's oceans. The analogy is seductive, but the sun is not a shallow ocean. It's a 15 million degree fusion core wrapped in magnetized plasma. You watch a sunspot group form, dark and brooding against the bright surface. Beneath it, a twisted magnetic flux tube has risen from deep within, buoyant and unstable. The timing of such emergences follows the broader solar cycle rhythm. And that rhythm, while roughly 11 years, varies in strength and duration. Some cycles last 9 years. Others stretch to 14. Some peak sharply. Others plateau. Historians still argue whether the variability contains hidden periodicities linked to planetary configurations or whether the patterns dissolve under rigorous statistical testing. The data sets are finite. The sun has only been systematically observed for a few centuries. That's barely a blink in stellar terms. You float outward again, while tracing the sun's looping barycentric path over decades. It forms elegant spirals and arcs, sometimes smooth, sometimes kinked depending on planetary positions. It's beautiful in its predictability. And yet the sun itself remains internally driven. Fusion in the core depends primarily on mass and temperature. Magnetic cycles arise from plasma motion and rotation. Planetary gravity may modulate motion slightly, but it does not supply energy to the core. So is anything truly pushing the sun? Perhaps not in the dramatic sense, not like a hand forcing a lever. But the sun is not isolated. Its motion through space, its wobble around the barycenter, its passage through galactic tides, all of these shape boundary conditions. And boundary conditions matter in complex systems. You settle back into the steady glow, or feeling the sun's immense inertia. It resists change. It balances gravity and fusion with extraordinary precision. Its magnetic storms flare and fade in cycles that predate humanity. Jupiter keeps pulling. Saturn keeps aligning. The barycenter keeps shifting. And the sun keeps responding. Not violently, not dramatically, but subtly, continuously, as any massive fluid body would when surrounded by companions. The dance persists, measured not in panic, but in patient geometry. And you remain there watching the wobble, wondering whether the smallest shifts in motion could echo deeper than we yet understand. You drift outward once more, past Jupiter's patient bulk and Saturn's pale rings, beyond Neptune's cold blue orbit, and into the thinning frontier where the sun's influence begins to blur. Here the solar wind slows. So charged particles that left the corona at hundreds of kilometers per second begin to feel resistance. This is where the heliosphere meets the galaxy. Picture the sun as a lighthouse wrapped in a vast, invisible bubble. That bubble, the heliosphere, is carved out by the continuous flow of solar wind pushing against the interstellar medium. For decades, scientists imagined it shaped like a comet, with a rounded nose and a long trailing tail. Recent data from missions like IBEX and Voyager suggest it may be more bubble-like, possibly even croissant-shaped. Yes, croissant-shaped. The universe occasionally sounds like it's designed by a very relaxed French astrophysicist. The mainstream fact is clear. The heliosphere acts as a shield, deflecting a significant portion of galactic cosmic rays. When solar activity is high, the solar wind strengthens and the heliosphere expands slightly. When activity weakens, it contracts. You hover near the heliopause, the boundary where solar wind pressure balances the pressure of interstellar space. Voyager 1 crossed this boundary in 2012. Voyager 2 followed in 2018. Their instruments detected a sudden drop in solar particles and a rise in galactic cosmic rays. It was humanity's first direct taste of interstellar space. And what they found was not a sharp wall, but a complex fluctuating boundary. The heliosphere breathes. During solar maximum, it swells. During solar minimum, it shrinks. This breathing changes how much cosmic radiation reaches the inner solar system. Now imagine that breathing combined with an external squeeze. As the sun travels through regions of varying interstellar density, the external pressure changes. If the solar system enters a denser cloud of gas and dust, the heliosphere could compress significantly. Models suggest that in particularly dense regions, far denser than our current local interstellar cloud, the heliosphere might shrink to within the orbit of Jupiter. That's not happening now, but it could have happened in the distant past or could happen in the far future. Historians still argue whether Earth's geological record contains signatures of such heliospheric compressions. Spikes in isotopes like beryllium-10 and carbon-14 suggest periods of increased cosmic ray flux. These are generally attributed to low solar activity rather than interstellar compression. but disentangling the causes is complex. You drift along the boundary, watching charged particles collide and scatter. When cosmic rays penetrate deeper into the solar system, they increase ionization in planetary atmospheres. On Earth, that can influence cloud formation hypotheses, though this remains debated and controversial. But what about the Sun itself? If external pressure compresses the heliosphere, the outer magnetic field lines may become more tightly packed. Magnetic reconnection rates at the boundary could increase. The heliospheric current sheet, the vast wavy structure extending through the solar system, might ripple differently under compression. Would that feedback propagate inward to the Sun's magnetic dynamo? Mainstream models suggest the core fusion engine would remain unaffected. The Sun's internal equilibrium depends overwhelmingly on its own gravity and nuclear processes. External pressure at the heliopause is tiny compared to pressures inside the Sun, and yet the outer magnetic environment influences how energy and particles flow away from the Sun. Changes in outflow conditions can alter angular momentum loss rates. The Sun gradually loses angular momentum through its solar wind, a process called magnetic braking. Over billions of years, this has slowed its rotation significantly compared to its youthful spin. If heliospheric compression altered solar wind structure, could it subtly affect magnetic braking rates? Possibly, but likely only marginally. Still, subtle accumulations matter over geological time. Here's a quirky tidbit. Some models suggest that if the heliosphere shrank dramatically, Earth might be partially exposed to direct interstellar neutral atoms penetrating deeper into the atmosphere. Imagine tiny interstellar messengers slipping through the shield, whispering tales of distant supernovae. Not dangerous in small amounts, but a reminder that the boundary is permeable. You watch as a ripple passes along the heliopause, triggered by a burst of stronger solar wind from a recent coronal mass ejection. The boundary flexes outward slightly, like a diaphragm inhaling. Breathing. The Sun's shield is dynamic, not static. It responds to both internal cycles and external pressures. Historians still argue whether long-term changes in heliospheric size correlate with Earth's climate cycles beyond the 11-year solar rhythm. The data is noisy. The climate system has its own complexities: volcanic eruptions, ocean currents, greenhouse gases. Isolating heliospheric influence is like trying to hear a whisper in a thunderstorm. Once you drift farther out beyond the heliopause and look back, the Sun glows at the center of a shimmering bubble, wrapped in magnetic threads. Beyond that bubble lies the galaxy, cold, sparse, but not empty. If the Sun enters a denser interstellar region in the future, its bubble will compress. Cosmic rays will surge inward. The magnetic boundary will tighten. It will not collapse the Sun. It will not extinguish fusion, but it will change the conditions at the edges. And edges matter in complex systems. You feel the quiet tension between inside and outside, between outward solar wind and inward galactic pressure. A balance maintained not by brute strength, but by continuous negotiation. The heliosphere holds, for now. But as the Sun continues its long orbit around the Milky Way, the interstellar weather will change. Clouds will thicken. Magnetic fields will shift. External pressure will rise and fall. And the Sun, steady, luminous, patient, will keep breathing against it. You drift back inward from the heliopause, carrying with you the memory of that breathing boundary, and now you turn toward something quieter, something frozen, layered, and patient. Ice, not the kind clinking in a glass, but ancient polar ice. Deep beneath Antarctica and Greenland, layers of compressed snow preserve a chemical diary stretching back hundreds of thousands of years. Tiny bubbles trap ancient air. Microscopic isotopes record invisible cosmic events. You imagine yourself descending through an ice core, layer by delicate layer, each band representing a year, sometimes even a season. It's like flipping through the Sun's scrapbook, except the Sun never meant for you to read it. Coronal, here's the mainstream fact. Isotopes such as carbon-14 and beryllium-10 are produced when galactic cosmic rays strike Earth's atmosphere. When solar activity is strong, the Sun's magnetic field deflects more cosmic rays, reducing isotope production. When solar activity weakens, more cosmic rays penetrate, increasing isotope levels. By measuring these isotopes in tree rings and ice cores, scientists reconstruct past solar activity. And what they found is fascinating. During the Maunder minimum, 1645 to 1715, carbon-14 levels rose, indicating reduced solar magnetic shielding. This aligns with historical records of fewer sunspots. Paintings from the era even show unusually vivid sunsets, likely influenced by volcanic aerosols. But the timing overlaps with low solar activity. Historians still argue how much the sun contributed to the cooler temperatures of the Little Ice Age. Volcanic eruptions clearly played a major role. Ocean circulation patterns mattered. The sun's reduced activity likely contributed modestly, but not single-handedly. Climate rarely has one villain. You drift forward in time through the ice layers. There are other minima. The Dalton minimum in the early 1800s, for example. Again, isotope spikes. Again, reduced sunspot counts. But there are also stranger spikes. Around 774 to 775 CE, tree rings show an abrupt increase in carbon-14, far sharper than typical solar cycle variations. A similar spike occurred around 993 to 994 CE. These are now known as Miyake events, named after the researcher who identified them. What caused them? The leading hypothesis is that they were triggered by extreme solar proton events, massive bursts of high-energy particles from the sun, far stronger than anything observed in the modern satellite era. Not supernovae, not gamma-ray bursts. Likely the sun itself, briefly exceeding expectations. If that interpretation is correct, then the sun is capable of producing eruptions stronger than the 1859 Carrington event, perhaps significantly stronger. You pause with that thought. The sun may not need external pressure to reach its limits. It may already carry within it the potential for rare, extreme outbursts. Historians still argue whether Miyake events were truly solar in origin or whether exotic astrophysical sources played a role. Current evidence leans strongly towards solar superflares. Observations of other sun-like stars show that some do produce enormous flares, far exceeding anything recorded from our sun. But here's the comforting detail. Those stars are often younger and rotate faster than our middle-aged sun. Stellar rotation strongly influences magnetic dynamo strength. The sun has slowed considerably over billions of years due to magnetic braking. Still, the possibility lingers that under rare conditions, magnetic fields could twist into unusually powerful configurations. You drift from the ice sheets to ancient trees, imagining growth rings quietly forming in forests centuries ago. Each ring a record, each isotope ratio a whisper from space. You begin to feel the pacing of this cosmic story slow slightly. The sun flares, the heliosphere breathes, the galaxy presses, ice remembers. The narrative is not one of sudden catastrophe, but of rhythms layered upon rhythms. 11-year cycles, century-long minima, million-year galactic oscillations, billion-year stellar evolution. You hover above Earth now, watching auroras ripple near the poles, soft green curtains trembling under solar wind. Beautiful, harmless mostly. And yet, if a Carrington-level event occurred today, modern infrastructure would strain. Power grids could overload. Satellites could malfunction. Not extinction-level drama, but inconvenient in a way that would make your Wi-Fi router seem tragically fragile. You smile gently at that thought. Humanity dependent on delicate electronics, orbiting a star that occasionally sneezes plasma. But the sun is not malicious. It is not being pushed in the emotional sense. It responds to physics, to magnetism. One to gravity. The ice cores tell you this. The sun has fluctuated before. It has quieted. It has surged. It has produced rare bursts that startled Earth's atmosphere. And yet, through all of it, it has remained stable in its core fusion. You let the imagery soften now. Picture the sun not as a raging furnace, but as a steady hearth. Flames rise and fall. Sparks occasionally leap higher than expected. The wind outside the house shifts, sometimes gentle, sometimes stronger. But the hearth remains built on deep stone foundations of gravity and nuclear equilibrium. The galaxy moves around it. Dark matter halos cradle it. Planets tug at it. Interstellar clouds brush its shield. And still, it burns. You begin to slow your breathing, matching the imagined rhythm of the heliosphere, expanding and contracting. The sun exhales solar wind, and the galaxy inhales around it. Ice forms, ice melts, trees grow, trees record. The story is not about a single force pushing the sun to collapse. It is about a network of influences pressing gently at its edges, testing boundaries, shaping cycles. You feel the warmth steady and constant, 5 billion years behind it, roughly 5 billion more ahead before it truly changes character and swells into a red giant. For now it is balanced. Pressured, yes. Embedded in tides and fields and gravitational dances. But balanced. You drift there in the glow, letting the scale of time stretch out like a quiet horizon. The sun does not panic. It does not hurry. It simply burns. And as you float in that steady radiance, you realize that whatever is pushing the sun is part of a much larger equilibrium, one that has held for billions of years. And the pressure is real, but so is the resilience. You linger in that steady glow, the memory of ancient ice still cool in your mind, and now you let yourself drift closer to the sun again, closer to the moments when it truly tests its own limits. Because while the core burns with remarkable stability, the surface and corona are another story entirely. You hover above a sprawling active region just as magnetic tension reaches a breaking point. Field lines twist tighter and tighter, braided by differential rotation and turbulent convection. For days, energy has been building invisibly, like a coiled spring wound past comfort. Then it happens. Magnetic reconnection. In a fraction of a second, field lines snap and realign. Energy stored in twisted magnetism converts explosively into heat, light, and kinetic force. A solar flare erupts, bright across X-ray and ultraviolet wavelengths. If you had eyes tuned to those frequencies, it would look like a flashbulb going off across a continent-sized region. Mainstream classification ranks flares from A to X, with X-class being the most powerful. The Carrington event of 1859 is estimated to have been at least an X10 equivalent, possibly stronger. In 2003, instruments recorded an X45 flare during the Halloween storms, so intense it saturated detectors. But could the sun go bigger? Observations of sun-like stars suggest that some produce super flares, hundreds or even thousands of times more energetic than typical solar flares. Data from the Kepler Space Telescope revealed that a small percentage of G-type stars exhibit these colossal outbursts. Historians still argue whether our sun is capable of similar super flares in its current evolutionary stage. Most evidence suggests it is far less likely, largely because our sun rotates relatively slowly. Faster rotation generally strengthens magnetic dynamos, increasing flare potential. Younger stars spin faster and rage harder. Still, the possibility of rare extreme events remains under study. You watch as the flare's energy ripples outward through the corona. Moments later, a coronal mass ejection follows, billions of tons of magnetized plasma hurled into space at speeds exceeding 1,000,000 kilometers per hour. If aimed at Earth, it would arrive in 1 to 3 days. Satellites would brace, power grids would prepare, auroras would dance far from the poles. You drift alongside the expanding CME, watching it balloon outward like a luminous storm cloud. Inside it, magnetic fields twist in complex spirals. When such a cloud collides with Earth's magnetosphere, the orientation of its magnetic field determines the severity of the geomagnetic storm. Southward pointing fields couple more strongly with Earth's field, allowing energy to pour in. It's less about brute force and more about alignment, like two magnets snapping together. Here's a quirky detail. During the 1859 Carrington event, telegraph operators reportedly saw sparks leap from their equipment. Some systems continued transmitting even after being disconnected from power sources, energized purely by geomagnetic currents induced in long wires. Victorian technology accidentally discovered space weather the hard way. Today, our wires are longer, our dependence deeper. But you return your attention to the sun itself. Each flare in CME represents the release of built-up magnetic stress. In a way, these eruptions are safety valves. They prevent magnetic energy from accumulating indefinitely. The sun does not endlessly store tension, it sheds it. Could something external amplify this buildup to dangerous levels? If heliospheric compression increased magnetic confinement at the boundary, perhaps coronal fields would adjust. If planetary gravitational rhythms subtly modulated internal rotation, perhaps certain cycles would peak higher. But mainstream solar models indicate that magnetic energy generation is overwhelmingly governed by internal plasma dynamics. The sun's convection zone churns continuously, driven by heat rising from the core. The dynamo regenerates magnetic fields in a self-sustaining loop. One and yet non-linear systems can surprise. You imagine the sun approaching the peak of a strong solar cycle. Sunspots multiply. Magnetic complexity grows. Flares increase in frequency. The solar maximum feels restless, crackling with activity. Historians still argue whether certain historical maxima were unusually intense compared to modern observations, given the limited instrumentation of earlier centuries. Proxy records help, but uncertainty remains. You drift just above the photosphere again, watching granules bubble like luminous cells. Each granule is about the size of Texas. It lives for minutes before dissolving and reforming. The scale is absurd, the energy relentless. And still, the sun holds equilibrium. Even the most violent flare represents only a tiny fraction of the sun's total energy output. As the fusion engine in the core continues undisturbed, surface chaos does not penetrate easily into that deep pressurized heart. You let the image soften. The sun is not a bomb waiting to detonate. It is a controlled burn, governed by gravity's inward pull and fusion's outward push. The flares are like sparks leaping from a campfire, spectacular, occasionally startling, but not signs that the logs themselves are about to explode. You drift outward with the CME, watching it expand and thin as it races across the solar system. By the time it reaches the outer planets, it will be far less dense, its magnetic structure stretched and diluted. The sun's limits are tested at the edges, at the corona, at the heliosphere, at the boundary where internal dynamics meet external environment. But the core remains steady. You feel that steadiness now, maybe like a low hum beneath the surface drama. A rhythm measured not in years, but in billions of years. The sun will not go supernova. It lacks the mass. It will not suddenly collapse under galactic tides. The forces are too small. It will continue flaring, cycling, breathing. You settle into that understanding, letting the scale of it calm you. The sun's most dramatic outbursts are spectacular, but not existential. Whatever is pushing it, galactic tides, dark matter halos, planetary tugs, it is not enough to break the balance. The limits are wide, the equilibrium deep, and as another flare blossoms briefly across the surface, you watch it with quiet appreciation. Not as a warning, but as part of the star's ongoing conversation with the universe around it. As you drift back from the fading coronal mass ejection and return to the deeper question that's been humming beneath everything. Not just what the sun does, but what it could do if nudged just a little differently. You let yourself imagine standing inside the corona again, surrounded by magnetic arches glowing like molten bridges. The sun's magnetic field is not static. It's regenerated constantly by the dynamo in the convection zone. Plasma rises, rotates, sinks, and rises again. Differential rotation stretches magnetic lines. Convection twists them. Reconnection releases them. It is a self-feeding system. But what if something external ever so slightly altered the core conditions? The fusion rate inside the sun depends primarily on temperature and pressure in the core. According to mainstream stellar physics, the proton-proton chain reaction is remarkably stable. If the core temperature increases slightly, fusion accelerates, producing more outward pressure, which causes the core to expand and cool. If the temperature drops slightly, fusion slows, gravity compresses the core, and temperature rises again. It's a built-in thermostat. This negative feedback loop is why the sun has remained stable for 4.6 billion years. It resists runaway change. Historians still argue whether any plausible astrophysical mechanism could significantly perturb this equilibrium on short timescales. The overwhelming consensus is no, not without extraordinary external forces, like a direct stellar collision or massive accretion event, and those are fantastically unlikely in our galactic neighborhood. Still, physicists enjoy asking uncomfortable questions. There are speculative models suggesting that certain exotic particles, like axions or other weakly interacting particles, could provide additional energy transport channels in stellar cores. If such particles carried energy away more efficiently, they could subtly alter temperature gradients. So far, observations of solar neutrinos and helioseismology align extremely well with standard models, placing tight constraints on such exotic effects. In other words, if something exotic is happening in the core, it's doing so very quietly. You drift deeper in imagination toward that 15 million degree heart. The pressure there is incomprehensible, about 250 billion atmospheres. Hydrogen nuclei collide and occasionally fuse, releasing gamma rays. Those gamma rays scatter countless times, and are gradually degrading into lower energy photons on their slow journey outward. It can take tens of thousands of years for energy created in the core to reach the surface. So even if something did change in the core today, the surface wouldn't know for millennia. That delay is oddly comforting. You pull back toward the convection zone again, where magnetic fields are shaped. This is where most of the sun's weather originates. If something were to push the sun toward more extreme flare activity, this is the region that would respond first. Could increased cosmic ray penetration alter ionization rates enough to subtly influence plasma conductivity? Possibly at tiny scales. Could gravitational modulation from planetary alignments shift rotational shear patterns? Theoretically, yes, but models suggest the magnitude is extremely small. Still, nonlinear systems can amplify small perturbations under certain conditions. The sun's magnetic dynamo is not fully understood in all its complexity. Simulations reproduce many features, but details remain active research topics. Here's a quirky observation. Astronomers have identified a handful of sun-like stars that produce superflares in historical Kepler data, despite having rotation rates similar to our sun's. That complicates the tidy narrative that only fast-spinning young stars flare dramatically. It suggests that under rare configurations, even mature stars might unleash unusually large outbursts. Historians still argue how directly comparable those stars are to our sun. Subtle differences in magnetic field topology or unseen companions might explain the discrepancy. You imagine, just for a moment, in the sun building an unusually complex magnetic region, twists layered upon twists, a configuration stable for weeks, then suddenly unstable. A flare 10 times stronger than the Carrington event erupts. Earth's magnetosphere compresses dramatically. Satellites fail. Power grids cascade offline. Civilization stumbles. But the sun continues shining, indifferent to Wi-Fi outages and stock market volatility. Because from the sun's perspective, even a massive flare is surface-level turbulence. The fusion core does not flicker. You let that image soften again. The sun is not fragile. It does not teeter on the brink of explosion because of galactic tides or passing stars. Its limits are defined by its mass. Only stars about 8 times more massive end their lives in core collapse supernovae. Our sun lacks the mass to do so. It will instead expand into a red giant billions of years from now, shed its outer layers gently, and leave behind a white dwarf. That fate is written in stellar evolution equations, tested against countless observed stars. So what, then, does it mean for something to push the sun to its limits? Perhaps it means pushing its magnetic dynamo to rare extremes, pushing flare amplitudes toward upper bounds, pushing heliospheric compression during unusual galactic conditions, but not pushing it into catastrophic collapse. You hover once more above the surface, watching granulation ripple like golden foam. The sun's light bathes Earth in steady brilliance. Photosynthesis hums quietly below. The limits are wide. The thermostat is strong. External forces, galactic tides, dark matter density shifts, planetary tugs, nudge boundary conditions. They influence context, not core. The sun's stability emerges not from isolation, but from feedback, from balance, from self-regulation. You feel that rhythm now, gravity pulling inward, fusion pressing outward, magnetic fields winding and unwinding, solar wind breathing against interstellar pressure. Whatever pushes, the sun pushes back. Not with drama, not with panic, but with equilibrium. And as you drift in that steady glow, you begin to sense that the real story isn't about imminent danger. It's about resilience under constant, gentle pressure from a dynamic galaxy. A star embedded in motion, balanced, burning. You linger in that steady burn, and now you turn toward the voices, the ones peering through telescopes, running simulations, arguing softly in conference halls about what all of this really means. Because the sun is not just plasma and gravity, it is also a debate. You imagine a room filled with solar physicists, astrophysicists, climate scientists, data analysts. Screens glow with magnetograms, helioseismic plots, isotope curves from ice cores. Coffee cups multiply like minor moons. Some argue that the sun's variability is almost entirely self-generated. The magnetic dynamo, driven by convection and rotation, contains within it all the ingredients needed for cycles, grand minima, and occasional extreme flares. No galactic puppeteer required. This is the mainstream position. The equations of magnetohydrodynamics, complex, nonlinear, occasionally rude, can reproduce cyclic behavior. Computer models simulate magnetic field reversals roughly every 11 years. Helioseismology confirms internal flow patterns consistent with dynamo theory. And yet, others explore correlations. Planetary alignments and barycentric motion, galactic plane crossings and extinction patterns, dark matter density variations, interstellar cloud encounters. Most of these researchers are careful. They do not claim cosmic doom. They ask narrower questions. Could weak external forcing synchronize internal cycles? Could long-period oscillations in solar activity align with orbital mechanics? Historians still argue whether statistical correlations between planetary torque and solar cycle amplitude are robust or artifacts of selective windowing. It turns out that when you have only a few centuries of detailed solar data, extracting long-term periodicities is tricky. You drift between these viewpoints like a neutrino passing through matter, rarely colliding, but absorbing perspective. One camp points out that stellar observations beyond our sun provide context. Thousands of sun-like stars have been monitored. Many exhibit magnetic cycles. Some show irregular variability. A few display dramatic superflares. This suggests that magnetic variability is intrinsic to stars of this type. External galactic influences are not required to explain most behavior. Another camp counters that no star exists in isolation. Even small external gravitational or magnetic fields can provide boundary conditions that shape internal evolution over long timescales. The sun's galactic orbit is not static. Its environment changes. Both views contain truth. You imagine the sun not as a machine on a lab bench, but as a boat at sea. Its engine is internal, fusion-driven, self-regulating, but the water around it still matters. Currents shift, and winds change. The boat adjusts. The question is not whether the ocean powers the engine. It does not. The question is whether the ocean subtly influences how the boat moves across time. Historians still argue whether prolonged solar minima, like the Maunder minimum, arise purely from internal dynamo fluctuations, or whether small external forcings nudge the system into those quieter states. Modern dynamo models can spontaneously produce grand minima without outside help. That strengthens the internal explanation. Yet the sun's barycentric motion during some minima remains an intriguing coincidence to some researchers. Coincidence. That word hovers like dust in a beam of light. You drift outward again, seeing the sun embedded in its heliosphere, embedded in the local interstellar cloud, embedded in the Milky Way's spiral arm. Embedded in a dark matter halo. Layer upon layer, each layer exerts influence, some strong, some faint. The core cares most about mass and pressure. The magnetic field cares about rotation and plasma flow. The heliosphere cares about solar wind strength and interstellar pressure. Earth cares about everything. You smile gently at that last thought. Humanity sits on a small rocky planet, building power grids and satellites, then looking upward and asking whether the galaxy is pushing our star to its limits. It's a very human question. Here's a quirky note. Early 20th century scientists once debated whether solar variability could be caused by planets blocking ether flows. The ether, of course, turned out not to exist in the way imagined. Science sheds old frameworks as evidence accumulates. Today's fringe may be tomorrow's footnote, or occasionally tomorrow's breakthrough. You watch as solar cycle 25 continues to climb in activity. Sunspots multiply, flares pop, nothing unprecedented, nothing apocalyptic. Just another crest in a centuries-long dataset, and yet monitoring continues relentlessly. Satellites watch in X-ray and ultraviolet. Ground-based observatories map magnetic fields daily. Neutrino detectors listen to the core in real time. If something truly began pushing the sun beyond known limits, we would likely see warning signs. Changes in neutrino flux, unexpected rotational shifts, anomalous magnetic patterns. So far, the sun behaves like a complex but stable system. Historians still argue how much we can extrapolate from a few centuries of precise observation compared to billions of years of stellar life. One, it's like judging a person's entire personality based on a few diary entries. You drift into a softer awareness now. The sun has limits, yes, defined by physics, by mass, by energy transport equations tested across the cosmos. But those limits are broad. External forces press, tug, compress, modulate. Internal forces dominate. The galaxy shapes the sun's path. Planets shape its wobble. Interstellar clouds shape its shield. But fusion shapes its fate. You let that settle gently. Whatever is pushing, the sun is part of a vast network of interactions, not a single villain in the dark. And as you float in the quiet between arguments, between data points and simulations, you feel something reassuring. The sun is not on the brink. It is in balance. Tested, yes. Embedded in motion, yes. Equal, but stable in the way only a star held together by gravity and nuclear fire can be. You drift a little farther out, letting the academic debates fade into the background hum of the universe, and now you allow yourself to ask the slightly dramatic question, what if the pressure grows? Not tomorrow, not next year, but over millions of years. You widen your view to the sun's long galactic journey. It orbits the Milky Way every 225 to 250 million years, weaving gently through spiral arms, oscillating above and below the galactic plane. With each crossing, local density shifts slightly. More gas here, stronger magnetic fields there, perhaps marginally higher dark matter concentrations near the midplane. Mainstream models show that these variations are modest at our galactic radius. The sun lives in relatively calm suburbs, shiny far from the chaotic inner regions near the galactic center. That's fortunate. Closer in, stellar densities rise dramatically and gravitational interactions become more frequent. But imagine for a moment that over tens of millions of years, the sun enters a denser interstellar cloud than any it currently inhabits. The heliosphere compresses significantly, perhaps even within the orbit of the outer planets. Cosmic ray flux increases in the inner solar system. Earth's atmosphere experiences elevated ionization. Climate feedbacks respond in complex nonlinear ways. Historians still argue whether past ice ages correlate with galactic spiral arm crossings. Some studies suggest timing overlaps. Others show mismatches once orbital uncertainties are refined. The data does not scream certainty, it whispers ambiguity. First, you focus again on the sun itself. If interstellar pressure increased enough to significantly alter solar wind structure, angular momentum loss rates could shift slightly. The sun might spin down marginally faster or slower over millions of years. Rotation influences magnetic dynamo strength. Magnetic strength influences flare frequency and amplitude. The chain is long, each link subtle, but over geological timescales, subtle effects accumulate. Now let your imagination stretch further, into rarer territory. Suppose a truly close stellar encounter occurred. Not 0.8 light-years away like Schultz's star, but 0.05 light-years. Still distant in human terms, but extremely close astronomically. Gravitational forces would strongly perturb the Oort cloud. Comet showers would increase dramatically. Would the sun's internal fusion change? No. But its motion through the galaxy might shift slightly. Its orbital path could alter by a tiny fraction, perhaps adjusting future spiral arm crossings by millions of years. These are not apocalyptic pushes. They are long-term nudges. You let the scale soften again. The sun's most dramatic future is already written, not by dark matter halos or passing stars, but by hydrogen depletion. In about 5 billion years, the core will exhaust its hydrogen supply. Fusion will shift outward into a shell. The outer layers will expand. The sun will swell into a red giant, likely engulfing Mercury and Venus, perhaps even Earth. That is the true limit of this star. It is set by mass. Historians still argue about the precise timeline of red giant expansion and how far the outer envelope will extend. But the broad picture is secure. Stellar evolution models match observations of countless similar stars at various life stages. So whatever pushes on the sun now, it does not alter that fundamental destiny. Still, you consider edge cases. Could an exceptionally dense interstellar cloud strip away the heliosphere almost entirely? Models suggest that if particle densities were thousands of times higher than current conditions, far denser than typical galactic clouds, the heliosphere could collapse dramatically. Such regions are rare and usually associated with star-forming nebulae. Our sun is not currently heading into one, but the galaxy is dynamic. Over hundreds of millions of years, spiral arms move relative to stellar orbits. The sun may encounter different environments. Would such an encounter destabilize the sun? Unlikely. The pressure exerted by interstellar gas, even in dense regions, is minuscule compared to the pressure inside the sun. You let that reassurance settle. The real vulnerability lies not in the sun's survival, but in ours. A significantly increased cosmic ray flux could affect Earth's atmosphere. A prolonged grand solar minimum could cool regional climates slightly. An extreme superflare could disrupt modern technology. The sun's limits are wide. Human infrastructure's limits are narrower. You hover above Earth now, watching city lights glow faintly on the night side. Satellites arc silently overhead. Power grids hum. Data flows invisibly through fiber and air. All of it depends on a star 150 million kilometers away, behaving mostly as expected. If solar activity intensified modestly beyond modern norms, technology would strain. If a Miyake-level event occurred today, or there would be serious disruption, but not planetary sterilization. The sun's limits are not the same as civilization's limits. Historians still argue how resilient modern society would be to a Carrington-scale event. Some predict months-long power outages in worst-case scenarios. Others argue grid protections have improved significantly. You return your gaze to the sun. It glows steadily, indifferent to stock markets and satellites. Whatever pressure the galaxy applies, dark matter gravity, interstellar compression, planetary tugs, it operates on timescales and magnitudes that rarely threaten stellar equilibrium. The sun is not fragile glass. It is a 1.989 times 10 to the 30 kilogram fusion engine. Its limits are defined by nuclear physics and gravity, not by passing clouds of gas or distant stellar neighbors. And yet, those neighbors and clouds still shape the context in which it lives. You drift in that understanding. If pressure grows, the sun will adjust. If magnetic complexity peaks, it will flare and release. If the heliosphere compresses, it will breathe against it. Balance may wobble, but it holds for billions of years more. You hover above Earth now, the sun blazing steadily behind you. And for the first time, the focus shifts fully to the fragile layer of technology clinging to this small blue world. Because while the sun's limits are vast, yours are more modest. You watch satellites sweep silently through low Earth orbit, communication relays, weather monitors, GPS constellations. Each one depends on stable conditions in near-Earth space. During periods of heightened solar activity, Earth's upper atmosphere heats and expands. And that expansion increases drag on low-orbit satellites, slowly pulling them downward. Mainstream fact: during strong solar storms, atmospheric density at orbital altitudes can increase significantly, forcing satellite operators to perform corrective maneuvers. In 2022, a moderate geomagnetic storm caused dozens of newly launched satellites to re-enter prematurely because atmospheric drag was stronger than anticipated. The sun did not roar. It merely exhaled a bit more vigorously. You drift through the magnetosphere, watching charged particles spiral along magnetic field lines toward the poles. When they collide with oxygen and nitrogen in the upper atmosphere, auroras bloom, greens, purples, reds shimmering like cosmic silk. Beautiful. But beneath that beauty, much geomagnetically induced currents can flow through long conductors on the ground. Pipelines, railway lines, power transmission cables. In March 1989, a geomagnetic storm triggered by a coronal mass ejection collapsed the Hydro-Quebec power grid in Canada within 90 seconds. Millions lost electricity for hours. Transformers overheated. It was not the end of the world, but it was a warning. Historians still argue how vulnerable modern interconnected grids are compared to those of the late 20th century. Some infrastructure has improved with monitoring and mitigation systems, yet dependency has grown exponentially. The more connected you become, the more you notice disruptions. You imagine a Carrington-level event striking today. High-frequency radio communications falter, GPS signals degrade, while satellites experience single-event upsets as energetic particles flip bits in onboard electronics. Power grids at high latitudes face strong induced currents. Transformers, large custom-built pieces of equipment that take months to replace, could suffer damage. Not extinction, but inconvenience at planetary scale. You smile softly at the irony. The sun's magnetic tantrums, trivial compared to its fusion output, become headline news on a planet that runs on electricity. Now widen your perspective again. Even during the most intense recorded solar storms, Earth's atmosphere shields life effectively from lethal radiation. The magnetosphere absorbs and redirects charged particles. At ground level, radiation increases only slightly. Astronauts in high-altitude flights are more exposed, yes, but the planet itself remains a sturdy cocoon. Historians still argue how often truly extreme solar proton events occur, those comparable to the 774 to 775 CE Miyake event. Estimates range from once every 1,000 years to once every several thousand years. The statistical uncertainties are large. You drift upward past the International Space Station's orbit, imagining astronauts sheltering in more shielded modules during a solar storm. Protocols exist. Monitoring systems watch the sun constantly. Early warning satellites stationed at the L1 Lagrange point provide about 15 to 60 minutes notice before a CME's magnetic shock front reaches Earth. 15 minutes. Cosmically speaking, that's less than a blink. Operationally, it's often enough to protect sensitive systems. You look back at the sun again. It appears serene from this distance. No visible hint of the complex magnetic machinery simmering at its surface. Whatever is pushing the sun, galactic tides, dark matter, interstellar compression, it does not appear to be driving it toward instability beyond known stellar behavior. Instead, what feels like limits are often human thresholds. Transformer tolerances, satellite shielding, grid redundancies. The sun flares, humanity scrambles. The star continues. There's a curious humility in that realization. Here's a quirky thought. If a Carrington-level event occurred in the pre-industrial era, most humans would have simply enjoyed spectacular auroras and perhaps some confused telegraph operators. Today, the same event would trend globally within minutes. The sun hasn't changed nearly as much as your dependency has. When you float gently back down toward Earth's night side, city lights glitter. Data pulses invisibly through undersea cables. Weather satellites track hurricanes. GPS guides airplanes across oceans. All of it nested within a magnetosphere, inflated by solar wind pressure. And that magnetosphere, in turn, nested within a heliosphere, breathing against the galaxy. Layer within layer, protection within protection. Historians still argue whether future technological societies will harden infrastructure sufficiently against extreme space weather. Some advocate transformer stockpiles and grid segmentation. Others trust probabilistic risk management. The sun does not care about risk management. It simply follows physics. You feel the quiet steadiness again. Even during solar maximum, even during geomagnetic storms, even during rare isotope spikes recorded in tree rings, the sun remains in hydrostatic equilibrium. The core burns with measured consistency. The magnetic fields twist and untwist. The heliosphere expands and contracts. The galaxy presses gently at the edges. And life on Earth adapts. You settle into that layered resilience. The sun's limits are wide enough to accommodate flares, CMEs, grand minima, and galactic drift. Human limits are narrower, but flexible. And as you drift between star and planet, you sense that the true story is not one of imminent stellar collapse, but of a dynamic balance, one that occasionally challenges technology, occasionally surprises scientists, but rarely threatens the star itself. The sun is being pushed, yes, but mostly at the margins. And at the margins, it knows how to bend. You drift upward again, leaving the glittering web of satellites and city lights behind, rising past the magnetosphere, past the orbit of the moon, until Earth becomes a soft blue marble suspended in black. From here, the sun dominates everything. It is easy, from the surface of a planet, to imagine your star as temperamental, flaring, spiking, occasionally disrupting your Wi-Fi like a cosmic prankster. But from this vantage point, you see the deeper truth. The sun is astonishingly resilient. It has endured supernova shock waves rippling through the galaxy. It has passed through interstellar clouds. It has oscillated through the Milky Way's disk dozens of times. It has felt the gravity of passing stars tug at its distant cometary halo. And through all of it, it has maintained hydrostatic equilibrium with extraordinary precision. Mainstream stellar physics tells you why. The sun's stability is rooted in feedback. Gravity pulls inward. Fusion pushes outward. If fusion increases slightly, pressure rises, the core expands and temperature drops, slowing fusion. If fusion decreases, gravity compresses the core, raising temperature and accelerating fusion again. It is a self-correcting system. Historians still argue about the fine details of magnetic dynamo behavior, about long-term cycle modulation, about correlations with galactic motion. But they do not argue about the sun's fundamental stability as a main sequence star. That foundation is solid. You drift closer, not to the flaring surface this time, but to the idea of scale. The sun contains 99.8% of the mass of the solar system. Jupiter, impressive as it is a rounding error by comparison. Galactic tides, although vast in reach, are faint at this distance from the Milky Way center. Dark matter shapes the sun's orbit, but does not buffet it like ocean waves. The forces pushing the sun are real, but they are small relative to the forces binding it. You imagine pressing gently on a cathedral made of stone. Your hand makes contact. Pressure exists, but the structure does not tremble. Its weight, its architecture, its internal stresses dwarf your effort. The sun is that cathedral. Its magnetic storms are like bells ringing in the tower, dramatic, resonant, occasionally startling. But the foundation remains unmoved. There's a quirky historical perspective here. In the late 19th century, before nuclear fusion was understood, scientists genuinely worried the sun might burn out within tens of millions of years. Geological evidence of Earth's age conflicted with the best energy estimates of the time. It wasn't until the discovery of nuclear processes in the 20th century that the sun's longevity became clear. Human understanding once underestimated the sun's endurance. Now, perhaps, it occasionally overestimates its fragility. You drift along the surface again, watching a sunspot group rotate calmly toward the limb. Solar cycle 25 continues its predictable rise. Not perfectly symmetrical, not perfectly timed, but well within known variability. Historians still argue whether future cycles may trend stronger or weaker over centuries. Some speculate about an approaching grand minimum. Others see no strong evidence for one. Climate scientists monitor, but they know that even a Maunder-level minimum would not override anthropogenic warming in the modern era. The sun is powerful, but it is not all-powerful. You widen your perspective further still, imagining the sun 5 billion years from now. Hydrogen exhausted in the core, helium accumulating, fusion shifting outward, the outer layers swelling. That is when the sun will truly approach its limits, not because of galactic tides or dark matter streams, but because of its own internal evolution. It will expand into a red giant, luminous and immense. Mercury will vanish. Venus will almost certainly be engulfed. Earth's fate remains debated. Historians still argue whether tidal interactions might cause Earth to spiral inward before or during the red giant phase, but that transformation is slow, predictable, and governed by mass and nuclear physics, not by passing stars, not by interstellar clouds. You feel a quiet reassurance settle over you. The phrase, pushing the sun to its limits, once sounded ominous, like something lurking in the dark, applying pressure to a star on the brink. But what you've discovered is subtler. The galaxy presses gently at the heliosphere. Planets tug gently at the barycenter. Dark matter curves space-time quietly in the background. Passing stars whisper through the Oort cloud. And through it all, the sun remains balanced. Its limits are defined from within. You float there, suspended between star and galaxy, and let the scale of it wash over you. The sun is not fragile glass. It is not a ticking bomb. It is a dynamic, breathing, magnetically complex, gravitationally bound fusion engine, embedded in a galaxy, yes. Influenced at the margins, yes, but fundamentally stable. And as you drift in that golden light, you begin to sense that the true story was never about imminent collapse. It was about perspective, about understanding the difference between pressure and peril, between fluctuation and failure, between being pushed and being broken. The sun, for now and for billions of years to come, remains unbroken. You remain there in the quiet, suspended between the sun and the slow swirl of the Milky Way, and everything feels calmer now. The alarms have faded. The dramatic music in your imagination has softened. What once sounded like a cosmic warning, something in space pushing the sun to its limits, now feels more like a lesson in scale. You watch the sun from a comfortable distance. It turns slowly, stately, sunspots drifting across its face like dark islands in a golden sea. A small flare blossoms at the limb, elegant and brief. Plasma arcs outward, then falls back in glowing loops. Nothing here looks desperate. Nothing here looks strained beyond endurance. Mainstream stellar evolution tells you exactly where the true limits lie. The sun is about halfway through its main sequence lifetime. It has fused hydrogen steadily for 4.6 billion years. It will continue for roughly another 5 billion before the core hydrogen runs low and structural changes begin. That timeline is not fragile. It is robust, calculated from nuclear cross-sections, measured in laboratories and confirmed by observing countless other stars at similar stages. Historians still argue about the fine details, exact red giant expansion rates, to the precise radius the sun will reach, the ultimate fate of Earth, but no serious model suggests that galactic tides, dark matter halos, or interstellar clouds will prematurely shove the sun into collapse. The sun's limits are written in its mass, and its mass is steady. You drift closer one last time, feeling the warmth, not the scorching heat of the photosphere, but the steady, symbolic warmth that has powered every ecosystem, every ocean current, every breath of oxygen you have ever taken. The sun has endured. Galactic oscillations through dense and sparse regions, close stellar flybys nudging the distant Oort cloud, planetary tugs shifting the barycenter, heliospheric compression and expansion, grand minima and magnetic maxima, Miyake events recorded in ancient trees, Carrington storms sparking telegraph wires, and through all of it, the fusion core has remained stable. Gravity pulls inward, fusion pushes outward, balance holds. You look outward again, past the heliosphere, into the dark matter halo and the faint glow of distant stars. Yes, the galaxy exerts pressure. Yes, interstellar clouds press gently on the sun's magnetic shield. Yes, giant planets tug rhythmically at its motion. But these are boundary conditions, not breaking points. It's almost funny, in a soft cosmic way. Humanity perched on a small rocky planet wonders whether something out there is stressing its star. Meanwhile, that star is so massive and self-regulating that even the entire planetary system amounts to a minor adjustment in its posture. A cathedral pressed by a breeze. You let that image linger, and now slowly you begin to soften the pace. Imagine the sun not as a roaring furnace, but as a quiet hearth in a vast dark hall. Flames rise and fall, sparks drift upward and fade. Outside, distant winds move across the galaxy. The building settles gently under shifting seasons, but the hearth remains. You breathe in. The sun breathes out solar wind. The heliosphere expands slightly, then relaxes. The galaxy turns. You don't need to brace for catastrophe. The physics is patient. The balance is deep. Even the rare extremes, super flares, grand minima, exist within wide margins of stability. And far in the future, when the sun finally does approach its true limit, it will not be because something external shoved it too hard. It will be because it has completed the long, steady work of turning hydrogen into helium. A slow transformation, a natural unfolding. For now, though, it shines, steady, resilient. We are embedded in motion but not undone by it. You let your perspective drift backward one final time until the sun becomes just another star in a quiet spiral arm. Billions of other stars burn in similar balance, some larger, some smaller. Many with their own planets wondering similar questions. The universe is full of pressure, but it is also full of equilibrium. And as you float there in the soft glow of that understanding, you realize something simple and comforting. The sun is being pushed, but it is not being pushed to the brink. It is doing exactly what stars like it are meant to do. Burning, balancing, enduring. And with that steady image warming the quiet space around you, you let the story settle into stillness. No alarms, no looming shadows, just a star in long, graceful equilibrium with the galaxy that surrounds it. Now, let everything slow. Picture the sun's light stretching gently across space, thinning as it travels, softening as it reaches the far edges of the heliosphere. The solar wind drifts outward in a quiet, continuous breath. Magnetic fields unwind and rewind in patient cycles. The galaxy turns without hurry. You feel smaller now, but not in a frightening way. Smaller in the way a single note feels within a symphony. Present, necessary, but held within something vast and steady. The sun does not strain against the universe. It belongs to it. Gravity holds it together. Fusion lights it from within. And all the subtle pressures, the tides, the clouds, the distant stars, are simply part of the environment through which it moves. Nothing urgent, nothing breaking, just motion within balance. So let your thoughts drift outward like the solar wind, in thinning, quieting. Let the questions dissolve into scale. Let the enormity of time smooth away the sharp edges of worry. The sun will rise tomorrow. It will flare and breathe and glow. And the galaxy will continue its slow, patient dance around it. You can rest in that.